can be thanked to by Christina, while herself cannot thank herself. So I'll just, before I pass the microphone, I'll just want to say big thanks to Christina. This event would not have happened without you actually taking lead of it. So now I will just withdraw. Christina, whenever you want to start.
Yes, thank you, Alex. And I also, of course, I want to thank Alex and Simon. This was really a group effort. I think we kind of assigned responsibility. So definitely, if this goes great, this is all of our merit. And also Nicholas in the a bit in the back, because he was dealing with so much at ICPE, but that meant he also had to deal with the things for several workshops and things like that. So that is actually the most heroic effort, I think. But anyway, welcome everybody to the 5th HotCloudPerf workshop. This year, I co-organized it with Simon and Alexandru, but prior years we've also had help from Nicolas and Alexandru Uta. And welcome everyone. And a super brief history. So HotCloudPerf began, or the idea of HotCloudPerf began in 2017 in the meeting with the SpecRG Cloud group at ICPE. And then this finally crystallized in 2018, the first edition. And this was with ICPE, like this year in Berlin. Then the second one was the ICAC and SASO conference in Umeå in Sweden, and that was the second edition. And then after that, we've had with ICP, 3rd, 4th, and 5th editions, which have been sadly online. We were hoping this year we could finally be able to, interact with everybody in the workshop, because the in-person workshops were definitely super great. But I mean, hopefully next year we can finally do that. And at least with the online things, it's nice that everybody can, like, sometimes the students and the professor can join, and like we have some sort of some benefits of doing that, right? And then we have videos too. So I mentioned the SpecRG research group, and within it there's the cloud computing group, and there's a link in there in the slides if you want to check more information, or if you want to join after you see the things that we do and the research that we do. You may be interested in doing that, so you can email any of us, or you can check the information in the link. The chair of the group is currently Alexandru Iosub, with the vice chair is Nicolas Herbst. And we have a secretary, which is Sachin Taluri, and a release manager, which is Andre Bauer. And what do we do in the group? Well, we basically take a broad approach to cloud benchmarking, quantitative evaluation, and experimental analysis. And we collaborate together in several projects that typically lead to publications in top journals, magazines, and conferences. And I can say from participating in this group that it's very exciting, because we have people from different universities. Let me change the slide. Okay, you can see it there. We have people from different universities all over the world, and also from industry collaborating. So I think that makes it a very enriching collaboration. And we can look at very interesting and cutting edge problems because of this. So again, the link is there. You can check it or send me an email. And we have a very interesting program this year. I'll be done with the introduction soon, so that we can have an introduction for the next session. And we have organized the schedule in 3 sessions. Each session has a keynote speaker, and our keynotes are both from industry and academia. And they're a bit loosely organized around a topic. So the first session that comes right after my introduction is the big data and microservices in the cloud, with a keynote from Paul Brebner, who's here with us now. And these 3 sessions are each separated by a very small short break. So you can, go eat something, go to a bathroom, and then the session 2 is optimizing data centers and development. And we also have an exciting keynote by Lydia Chen. And then the session 3 is on the subject of serverless computing, with a keynote from Evgenia Smirny. And at the end, we like to have a discussion, and we did this when it was on site. Like we maybe have a poster session or go somewhere to talk. And with the virtual conferences, we've also been doing this, where we basically, people can join and talk about like what they're doing, or maybe if they want to join, they can come and talk to us about joining the group, or basically just some social, chatting, so we have a nice ending to the workshop. And also, Alexandru mentioned this at the beginning, but if you joined a bit late, all discussion is going to be happening through Slack. And you should go to the ICPE Slack when you registered, and you've received that link in several emails. And once you go to the ICPE Slack, there's a channel for each of the workshops, and ours is ICP22 WS for workshop and HotCloudPerf. If you go to that channel, you can chat with everybody, but more importantly, you can ask questions to the presenters, because we won't be using the Zoom chat, only that one. If you haven't done it, if you haven't already checked the Slack, you should do it right now, so that whenever you have a question, you don't have to solve technical issues at that moment. So you can just go and post a question. So that's basically it. I welcome everybody that's here, and that means lots of people that are on crazy schedules right now. Some people, it could be very early, very late, or it could be at the perfect time, but then it becomes late later on. So definitely, this is it's very nice to be able to see everybody here, and we have a nice audience so far. And yep, that's it. And feel free to ask also any of the co-organizers direct questions via Slack if you have something specific that's not for the group. So with that, I will end my presentation. I will stop sharing. Hold on for a second. I should go. So I'm doing this stop share. Yes. So that's done. And so we can now, we have time. So Paul can share his slides.
Okay, let me just, hopefully this will all work. I'm not a Zoom expert. So let's see what happens here. Eeny, meeny, miny, mo. Let's pick that one and see what happens. Hopefully that should all work correctly. Ooh, oops, what's going on there? Okay, is that working okay from your end?
Yeah, this looks good. We can see the top row, but it should be okay. Can you maybe try switching a slide if that also works?
Okay, so you can't see the whole screen, or?
Oh, we can see the whole screen. We can just see the row from the window, but that's fine. This looks good. All right.
Okay, cool.
I'm honored to introduce our first keynote speaker today, which is Paul Brabner. He's currently the technology evangelist at Instacluster. In the past, Paul has worked in the distributed systems and performance engineering research and development at Cicero UCL and Nikita ANU, and he's also been the CTO in a startup that's focusing on performance modeling from APM data. Further, he's been involved with ICPE since 2011, and we're excited that he will present a keynote today with the quite interesting title, Scaling Open Source Big Data Cloud Applications is Easy/Hard. So I'm excited to see what hides behind this title.
Thank you very much. Thank you all for organizing the workshop this year. It's an honor to present. Thanks for the invitation and the opportunity to talk. Let me just hope this works correctly. There we go. I apologize for the vision here. I actually bought myself a new web camera a few days ago and discovered that it's very power hungry, and if I plug it into my Mac, it causes everything to fail, including the mouse and the keyboard. So I had to revert back to my old-fashioned inbuilt one. So I'm the technology evangelist at Instacluster. I'm based in Canberra, but Instacluster is a global company. So I spent probably the last 5 years, I guess, with Instacluster learning new sort of open source technologies as they're brought onto our platform, building demonstration applications, writing lots and lots of blogs, giving quite a few talks, mainly at industry conferences these days, and occasionally sneaking some performance engineering in as well. So hopefully this is of interest to the workshop. who am I? You've stolen some of my thunder here. I was impressed that you knew so much about me. And it actually was, I think it was 2011, the first ICPE conference I went to. So I went to quite a few after that, but I've had a bit of a holiday from ICPE, as probably most people have in terms of attending physical conferences the last few years, unfortunately. So originally I was doing quite a lot of enterprise Java evaluation with Cyro. I was involved in the Spectre app server a couple of times from memory. I worked at UCL for a while doing grid evaluation and benchmarks. And then as part of the Nectar research group, we were doing R&D and consulting and performance modeling, large-scale distributed systems for government and large enterprises mainly, and that resulted in a startup for a few years. I've been with Instacluster since 2017. Unfortunately, preparing this talk yesterday, there was a very large interruption, which was the announcement that we're actually being bought out by a large American company called NetApp, which is now public news, but it was news to me yesterday, and it resulted in quite a lot of chaos, unfortunately. So I spent most of today preparing the slides instead of having them all ready by yesterday. So yeah, I've written lots of blogs. I haven't done much in the way of academic publication for the last few years, but hopefully there's something interesting here that might spur some research on the back of some of the problems that I talked about. The performance modeling stuff I did when I was a Nectar and a startup. So we actually took APM data from Dynatrace's pure paths, transformed that into a performance model, and then executed that in our own simulation tool, which could do model visualization and graphing as well. So it was a predictive analytics sort of pipeline. It was automated. It only worked with Dynatrace pure paths in spite of our attempts to get it to work with other APM vendors. There just wasn't enough information in the traces available from other vendors to get it to work. So that was one of the limitations with it. It's interesting, there's been quite a growth recently in some of the open source monitoring and tracing technologies like Prometheus and Open Tracing, which have now been combined in a new standard called Open Telemetry that you've probably heard of. I reckon it could be worth revisiting this type of automated performance modeling using Open Telemetry, maybe supplemented with a few other clever tricks to get some of the missing data if anyone would like to have a go sometime. Just a bit about Instacluster. We have basically a managed platform. It's a cloud platform for big data open source technologies. We've got things like Cassandra, Kafka, Spark, OpenSearch, which is the AWS version of Elasticsearch. And a new one that we've just added actually recently, which is quite interesting, is a highly scalable workflow engine from Uber called Cadence, which is quite fun. It's quite a clever technology. So, okay, the talk's really about scaling. Scaling is easy. Cassandra and Kafka, in particular, are two of our main technologies we offer for customers as a managed service. They're actually very well designed in terms of scalability from a hardware perspective. Each of the nodes in a Cassandra and Kafka cluster are homogeneous. They all are equal. There's nothing special about any of the nodes. They're a distributed system. You can just add more nodes and you get horizontal scalability. Some of our customers run small clusters with 3 to 6 nodes. Others have hundreds of nodes in them, which is quite complicated to manage. Cassandra is a NoSQL distributed database. Kafka's for a streaming messaging type system. It's a bit more complicated though. There's actually quite a lot of moving parts in these technologies. So just like an old-fashioned steam engine, everything's actually got to work well and it's got to be oiled correctly, otherwise something probably will go wrong inevitably. So there are some complications in running these types of systems. There are often multiple data centers. Each data center often has multiple racks, which are sort of redundant systems, sort of like mini data centers in terms of the cloud providers terminology. There's multiple nodes, which are essentially multiple servers running parts of the cluster. And just to make matters worse, there are things called partitions, which essentially for Cassandra and Kafka are what gives it the real scalability and concurrency under the hood. There's also replication, the replication factor, which gives you the redundancy of the data, so it'll cope with failures and give you high availability. And then there's also time to take into account as well, particularly for any scaling actions. It will take time to scale the clusters, basically. So this is a bit of an architecture diagram of some of those aspects for Cassandra. Cassandra basically maps rows onto different partitions using a partition key. And that results in the data being stored in different partitions on different nodes, on different racks, and potentially on different data centers. So that's a bit of an overview for people that perhaps aren't all that familiar with Cassandra. So I'm going to look at a couple of different sort of use cases or examples of things that I've done over the last couple of years where I think there's an interesting performance engineering story, often a problem, and hopefully some insight into what's going on with some of these cloud technologies. So the first one I'm going to have a look at is one I did quite a long time ago. So I hope you don't ask too many tricky questions because I probably can't remember much more than what I've got in the slides here, but it's a Cassandra auto scaling example. And if you type in Cassandra auto scaling or Cassandra elasticity into Google, you probably won't get many hits, and that's because typically you actually don't auto scale Cassandra, but we do sort of. So there's actually two ways of resizing clusters in Cassandra. There's horizontal scaling, which is just where you add nodes. There's no interruption to the system, but you can only scale up, not down. That's a fundamental limitation. It takes time and it puts extra load onto the cluster as data streams to the new nodes that you've added. There's also vertical scaling, which is what I'm going to talk about. This is where you replace nodes with bigger or smaller, potentially node types with more or less cores. So you can scale up and down, which is an advantage. But again, it does take time and there's a temporary reduction in the capacity of the cluster as you do it. There's a choice as well. There's a choice of how many nodes are replaced concurrently. The terminology is by node, which is one node at a time, or by rack, which is all of the nodes in a rack at a time, basically concurrently. Or in fact, there's an in-between option as well, which is an arbitrary number of nodes. So here's a graph of some experimental results I did quite a while ago. This shows the cluster resizing time for resizing by node on the left versus resizing by rack on the right. What do we notice? Well, resizing by rack is certainly a lot faster than resizing by node. That's due to a whole number of things, but basically it is because of the extra concurrency you get that you can replace more than one node at a time. So resizing by rack is faster, but let's have a look. Resizing by node, what happens? So this graph shows what happens in terms of the capacity reduction briefly, which occurs when you get 1/6 of the total nodes each resize operation. So this is a very simplified model. This times on the x-axis and on the y-axis we have the capacity of the cluster in terms of percentage. It starts out at 100% and eventually ends up at the green dotted line, which is 200%. So we're doubling the capacity. You can do more than that at a time, but this is very simplified models to see what's going on. And resizing by rack, you get the capacity reduced by 2 out of 6 because you're losing 2 nodes each time as a result of resizing by rack. So it does happen faster, as you'll notice, but you get that bigger reduction in capacity initially. And this graph shows both of those results on the one graph. So it's easier to see that resize by rack is certainly faster, but does have a bigger capacity hit during the resize operation itself. So just a few observations. In both cases, the eventual capacity is double the original. The cluster capacity is reduced during resizing. By rack is faster, but has worse capacity reduction during resizing. By node is slower, but has less capacity reduction during resizing. If the capacity during the resize is exceeded, latencies will increase. And this is actually made worse by the Cassandra load balancing, which assumes that every node is of equal size. So during the resize operation, things really won't work particularly well. Resizing by node, more nodes in the cluster reduces the impact of the reduced cluster capacity during resize. It's sort of obvious. And some of our customer clusters have hundreds of nodes. But it actually turns out the majority of our customer clusters actually have less than or equal to 6 nodes. So there is, this makes it more relevant in a sense for a real case. So what would an auto-scaling model look like? So this graph shows an hour's measured data where the load is increasing pretty linearly. That's the measured arrow there. And we've applied some linear regression over that data, extrapolated into the future to see when we expect the cluster to reach 100% capacity. So in this case, we've predicted the cluster will reach 100% capacity around the 280-minute mark, which is 220 minutes into the future. What can we do? Well, this graph shows the difference between resizing by rack versus node, where you initiate the resize operation in time to prevent overloading during the resize operation itself. So this is the tricky bit in a sense. So resize by rack must be initiated sooner compared to resize by node. So this is the case even though it's faster to resize by rack. The problem is it has less capacity during the resize. So for the particular sized cluster and rack size and everything that I picked for this example, it's 67% versus 83% of the initial capacity. So we built an auto-scaling proof of concept just to see if we could turn some of these ideas into something that customers could potentially use. To my knowledge, no customers have actually used this, but we did demonstrate that it was possible and documented it so they could try it out. So we provide a couple of different APIs to our systems. There's a monitoring API, which gives an awful lot of metrics at the cluster level and lower as well, even at the node level. There's also a provisioning API. So typically, a lot of customers just use our sort of GUI console for doing provisioning, but there is actually an API, which means people can automate provisioning for DevOps and also for cases like this where you may want auto-scaling, for example. So what we did was take the monitoring data out of the API, put it into Prometheus, which is an open source monitoring infrastructure. Then we applied the linear regression to the data and some rules that we came up with in terms of what sort of resizing to perform and when, and if there were any exceptions that people needed to be alerted about, because you can't always resize in the way that you want, and there just may not be enough time to do it as well. So Prometheus actually provides support for both the linear regression and the rules, so that was great. And then that feeds back into the provisioning API. It makes, once you've made the choice about what to do, basically we tell the provisioning infrastructure to increase the size of the cluster in a particular way or a particular concurrency level. So we come up with some rules that were generalized to allow for scaling up and down and resizing by any number of nodes concurrently up to the number of nodes in the rack. So it was a pretty general solution and it did work quite well. So that's a very brief and quick overview of the first example. Example number 2. This is another project, probably my second project actually logically, that I did for Instacluster, where I built a demonstration Kafka application. And the focus of this example is on Kafka topics. It was called Congo. It's a logistics IoT application. It was based on transportation of goods to and from warehouses in trucks, with lots of rules around what was allowed to be transported with each other and sensors which provided data about the environment so that you could check if anything had exceeded any conditions for transportation, and simulated RFID interfaces as well so that you knew where the goods were at all times as well. So that was sort of the story, and building it was sort of interesting. So Kafka is a topic-based pub-sub messaging system. You can have multiple producers sending messages to multiple topics, and you can have multiple consumers subscribing to multiple topics of interest. In this case, there's a whole bunch of consumers that are interested in parties, but they're not so interested in work, for example. The consumers actually poll the Kafka cluster. That's the way it works. When they poll, they only receive messages sent to those topics. So the topics really are the filtering mechanism in Kafka, which enables messages to be sent to the subscribers that are going to be interested in those particular messages. Okay, so there were a couple of design choices, particularly because I was new to Kafka. It wasn't obvious whether you should have many topics or one topic or something in between. And again, this is a bit of a simplified overview, but basically we're looking at the question of whether you should have many topics, which corresponds to the idea that there's hundreds of locations in terms of different warehouses and truck locations. So each location in the first design has a topic, and multiple consumers subscribe to that topic, which means you end up with an awful lot of topics in the system. The second design choice was really having one topic for all the locations. So essentially, this design variant means that you've got one or more consumers all subscribed to the one topic, and you've got to do something a bit clever and tricky on the other end to make sure that the recipients get only the messages that they're interested in, rather than using Kafka itself to do that. But it did allow us to look at these two different choices and see what the result was. And the result was actually quite significant. So this single topic design wins by an awful lot. So this shows the difference in throughput for sort of an average sized Kafka cluster. We're getting about 1 million transactions a second through with a single topic, and not very many at all through the system that had hundreds of topics. So there's obviously a big difference in terms of this design choice. And at the time I was building this demonstration, I didn't think much more than this about the problem and didn't try and understand what was going on. We just ended up building this and getting some quite impressive numbers, but I didn't really understand what the impact of having multiple topics was on Kafka at that point in time. So the third example was another system that I built to do scalable anomaly detection. I thought this was a very interesting view of the world back in the 60s. It shows a very male-dominated mission control with one woman there, apparently. So yes, anomaly detection. This one involved multiple technologies, Kafka, Cassandra, and Kubernetes, which is sort of a cloud native approach for enabling applications to be deployed into different clouds and scaled really easily, maybe too easily in hindsight perhaps, but so we had at least these three systems all working together and integrated together. So it was massively scalable anomaly detection. This is a bit of an overview architecture diagram of the system. So the knobs sort of indicate the things we could change or tune. Some of them are hardware knobs. The orange ones are more or less the size of the types of clusters that we have in the system, and the yellow ones are some of the critical software settings that needed to be tuned eventually. So the system works by generating load as having a Kafka producer, or in fact multiple Kafka producers going into the Kafka cluster producing events. There's an anomaly detection pipeline, which initially started out just as a whole bunch of Kafka consumers, which read those events. They immediately wrote the event into the Cassandra cluster, and then got some historic data related to that event. So there was quite a lot of data being read back at that point into the pipeline. It would run the anomaly detection algorithm and then say yes or no in terms of whether it thought an anomaly had occurred. So we initially found that scaling was actually pretty easy. All we had to do was just increase the size of the Cassandra, Kafka, and Kubernetes clusters. And we thought, wow, that's easy. We're going to get some really impressive scalability performance results. So actually not so great, unfortunately. It was a lot worse than we expected in terms of scalability. It was really it dropped off significantly as we added more cores to the whole system. We just didn't get the scalability that we were expecting. So the final system we got up to was about sort of like 580 cores spread across all those three technologies. Cassandra was by far the biggest number of cores, followed I think by Kubernetes, which is running the actual application pipeline, followed by Kafka, which actually wasn't all that big for a system this size. So what did we do to improve this? Well, we had a bit more of a rethink, and we actually ended up tuning the system progressively as we increased the hardware resources. So tuning was required. This shows the result post-tuning, which was a lot better. We got up to 19 billion anomaly checks a day on that size system, which was relatively impressive. Demonstrated that the system was quite scalable. As you add more hardware resources, you do really get more throughput through the system as expected. And how did we do it? Well, we had to optimize software resources, basically. So in this diagram, again, it's the red arrows this time that we had to optimize. And again, this was more or less an experimental approach for understanding the performance and throughput of the system. We didn't necessarily at this point understand why these things were important. It just turned out that these were the ones that had the biggest impact on the scalability. So the first thing we had to optimize was the number of Kafka consumers. Initially, we just had the one big thread pool, which meant we had lots of Kafka consumers. So we split the Kafka consumers essentially into 2 thread pools. So we ended up having to minimize the number of Kafka consumers by making thread pool 1 as small as possible. But we then had, well, we also wanted to minimize the number of Cassandra connections. That turned out to be relatively important. You shouldn't have far too many than you need in terms of Cassandra connections. It wasn't the biggest thing, but it was important. And third was to maximize the number of Cassandra, the concurrency in the Cassandra client part of the pipeline, which meant increasing the size of the second thread pool, basically. So what we've done is decouple the Kafka consumer really from the rest of the pipeline. At the time, it felt like a bit of a hack, but it certainly solved the problem in terms of getting that scalability and throughput that we wanted. But it turned out basically we needed to minimize the number of Kafka consumers, but still managed to have the maximum concurrency in the rest of the system as required. So the final example, so I do see all the questions. I'll get to those in a second.
You get started on the final example.
Oh, yeah.
We have about 5 minutes in the session left, including questions.
Right, okay.
So depending on how long this example is, you might
I think I'm getting to the end. So, okay, I'll speed up. So, okay, example 4, what's really going on behind the Kafka petitions? You never know what's going on behind the petitions. So yeah, it turns out that petitions are the key in Kafka. In Kafka, topic petitions enable consumer concurrency. So this diagram shows that basically you share the work between multiple consumers by having more petitions than the number of consumers. So as the number of consumers goes up, the number of petitions has got to go up even more, basically. Fan-out requires many consumers and petitions. So this can be caused, as we mentioned already, by design. You can choose to have many topics and consumers, or Little's law, in fact, comes into play as well. So in the anomaly detection example, the number of consumers is basically the time spent in each consumer times the throughput. So slow consumers require more consumers to keep up the target throughput. And having the 2 thread pools essentially was solving this problem and reduced the consumer time and therefore the consumer count. This diagram explains the Kafka write architecture. Essentially, every message written to the leader petition is also replicated into the number of follower petitions that you want on other nodes. So there's actually a lot of overhead in terms of the replication of events due to the petition and replication architecture, which benchmarking revealed that the combination of petitions and replication factor are the real culprit in terms of limiting throughput in the Kafka cluster. So the orange line here sort of proves the point. Replication factor is 1. You can have as many petitions as you like. It doesn't affect the throughput. As soon as you have the replication factor set at 3, which is basically required in a production cluster, you get a significant drop-off in the throughput in a Kafka cluster, which is the blue line there, which was essentially the underlying cause for all of the Kafka performance issues that we've seen in the other examples. Implications, well, you can throw more hardware at it. It costs more money, but it does fix the problem. Try and optimize for the minimum number of topics and consumers and the minimum consumer time. I've seen a lot of benchmarks and reviewed papers that have benchmarks of Kafka with 1 petition. No, it's not really any good. You need multiple petitions for benchmarking Kafka to see what the real performance is. And Apache Zookeeper is actually currently used for the control plane of Kafka. That's being replaced soon, and it's possible that replacement protocol may actually result in better throughput in Kafka clusters with more partitions as well. Example 5, just kidding. This is another one I was going to talk about. It's a data pipeline with multiple technologies. Check out the blogs. There are some interesting performance problems with that as well. And if I can stick in a bit of free advertising, what do you get when you combine ApacheCon with Bullet Train? Basically, it's an open source performance engineering track, which we're trying out this year at ApacheCon for the first time. There's the link for it. We're looking for any sort of papers on open source performance engineering, particularly ones that apply to Apache software or use Apache software to solve other performance engineering problems. Thank you very much. So all of the talk today was actually excavated from all my blogs, which are at that URL there. So some of the blogs are in a series, so you need to sort of look at a couple of different blogs to pick up the story and find the relevant section that talks about the performance aspects. Well, that's all I've got to talk about. So over to questions, I guess.
Thank you very much for the interesting talk. You could also copy the links you have in the Slack to make them a bit more accessible.
Okay.
With a quite large set of questions for you, actually. That
Okay,
we probably won't get through all of them, but you can also answer them later in the Slack as well. So the first one is from Alexandru. Do you maybe want to ask this yourself?
I can, sure. I'm actually not sure which one to ask, but
your favorite.
Sure. Let me start with a question that I find very important, because we get asked this question quite a few times. You're building proofs of concept for various situations, and my question is, what are the challenging aspects in your experience of taking these proofs of concept and actually putting them in production with your customers? How big is the difference?
Okay, yeah, there is a big difference, I agree. Essentially, we're trying to inspire them rather than giving them a definitive, correct best practice necessarily. So at least that's my job, is to come up with sort of inspiring, slightly exciting use cases and show that it's certainly possible to build a highly scalable performing system that doesn't cost the earth. And then, yeah, they hopefully will take some of the ideas and go away and build their own system. I mean, we've got quite big customers using us. I can't remember which ones I'm allowed to say, but there's quite a few large delivery customers like Uber, for example, but not Uber. And they've got mission critical stuff running on these open source technologies. Yeah, that makes sense.
Right,
it does. It also seems like there's still a significant and at least engineering effort, and that is still the burden of the customer.
Oh, yeah, absolutely. Look, so getting the application right is hard. That's what I found. You have to have the right design. You've got to do benchmarking. You've got to configure it correctly in the production environment, and you've got to monitor it and cope with unexpected behavior, including problems where the load goes up and you've got to increase the size of your cluster. So it's not, none of the stuff is magic. Unfortunately, it certainly requires significant effort, I think. But I guess doing it myself, I'm the guinea pig. I've done it. I can help them by documenting what things to watch out for and things like that. So yeah.
Right.
The question about linear regression, that's an excellent one. Not very well in practice is my guess. Yeah, linear regression has certainly limitations. From some of my previous performance modeling predictive work, we tried non-linear regression approaches, and they work very badly in reality as well. So I don't know what the solution there is, to be honest.
So could you stop your screen share so Floriment can take over? And while he's setting up, have you considered time series forecasting methods for this predictive thing? Because I think this is something that's also commonly used there. instead of regressions?
Haven't tried that. I guess we just use whatever Prometheus sort of provided for free, more or less. And because it wasn't for a particular customer or anything, it was we didn't actually have to get it working for real. So yeah, that's a good idea. Yeah.
Maybe you can go through the leftover questions in the Slack, and then we can start with the next talk by Florian.
All right, thanks for that, everyone. I hope it was relevant and interesting. So thanks for your time.
Thank you. Let's thank the speaker. It's a bit different, right? In the online world, we can only put these virtual applauses.
Simon?
Yes, we can see your screen well, so feel free to get started. Again, another talk with a very promising and interesting title.
Okay, thank you very much. My name is Florian Klinaco. I come from University of Stuttgart, and this is a joint research work with Martina and Jörg from FZI and Stefan from Bosch. And I think the previous talk quite gave me the motivation for starting easier. So this work originated from the motivation that scaling microservice apps remains a challenge. And this is due to several factors. One is, for example, the uncertainty in the execution environment. Another thing is that systems are getting bigger in terms of the number of components that need to be controlled, and they influence each other. So we are researching whether we could help the architect to do more reasonable design decisions by using model-based performance prediction techniques, so that she can model the initial architecture and then model various scaling alternatives and choose the best performing one. In this context, we were looking for a reference use case to validate our ideas. And when we checked, some of them were lacking some features that were important for our industry partner. For example, synchronous communication. And another requirement was that we can generate a reliable load generation that serves us in reproducibility, but also it makes our life easier when comparing it to the models. So this is why we designed the remote measuring reference use case. And the remote measuring reference use case offers two interfaces, one for the devices and one for the users. And the devices send context data, location, and etc. And the users analyze and retrieve those data via an API. In our remote measuring reference use case, we built our beautiful and innocent services using Spring Boot. And in addition, we used Protocom, which is a library to generate CPU workloads for arbitrary hardware. So by using Protocom, we can simply tell the library, look, I would like to have a demand for processing an item of 1 second, for example. And then Protocom makes sure that it generates the workload for the CPU that takes that amount of time. And In addition to this, we were using MongoDB as a persistence for some of the data that were coming from the devices, and the services were using RabbitMQ for communication purposes. And here comes the beast, a Kubernetes cluster with 7 nodes provisioned on BW Cloud. And although we used Protocom, we experienced large deviations from what we expected. So then we said, okay, this needs further investigation. And then we were wondering why and what is causing that. So the rest of this talk focuses more on these experiments, and those of you that are interested to know more about the reference use case, you can read on the paper. So what we did, here is the beast, and the nodes were same in terms of the flavor, but of course different workloads were executing on them. And we designed another beauty, and this time we wrapped Protocom with a Java micro-benchmarking harness framework, and we varied the demand. So we chose like 3 different levels, 50, 200, and 1000 milliseconds. In addition to this, we used OpenCruise to help us with automating the experimental workflow. And there we defined this broadcast job that makes sure that the same container image is executed on all the nodes, and it waits until they complete. We did 5 runs per configuration, and each run was taking 30 to 40 minutes, including the calibration time that Protocom needs. And last but not least, we analyzed the results. But what is a configuration in our case? A configuration is a point in the configuration space consisting of 3 dimensions in this context. One is the quality of service strategy that we can use for our benchmark container. And there we use 2 different strategies like best effort and guaranteed. Another dimension is the cluster compilation itself, because our cluster might be at different times in different state. And sometimes the change in state is induced by us, for example, restarting the nodes. And sometimes it is induced by the cloud provider itself, where they, for example, do maintenance work and so on. And the last dimensions are the load levels, where we did experiments on 3 different load levels, which I will tell you shortly about that. We explored this configuration space in a more iterative way. So initially, we started with the best effort class and in a low loaded scenario, meaning that in the cluster, there was no additional stress being executed. And then we were quite surprised with the results, and we decided to do another replication. And we did this replication after we rebooted all of the VMs. But not much changed. So we said, okay, what about if we use the guaranteed quality of service class, whether it will improve the variability of the results. But even that did not matter in this case. So what you see now is the overall variability of our results for those 3 initial series of experiments. And they look quite consistent, and they look much worse compared to a local execution of Protocom. So what we then did is we checked closer at the results to see, okay, how do they look on a per node basis? And as you can see, some nodes are performing quite well, like node number 6, whereas the node number 2 has quite a large variation. So we were thinking, okay, maybe this is somehow correlated to what is being executed on the cluster, because it happened that on node number 2, we had the Rabbit broker running, and it had the highest usage of millicore. And on Minion 6, or node number 6, we had quite a low usage and no characteristical pods were running there. So we computed the correlation, and although the Pearson correlation coefficient suggests a slight positive correlation between load and the coefficient of variation, the plots itself show that we can't conclude that, and that more data is needed. For example, if you see on the left plot, we miss quite some data points in the range between 280 and even more. The last set of experiments were done after a major BW cloud maintenance, which happened early March this year. And they did many things there. One of them was they updated the OpenStack. So they changed the OpenStack release. And I intentionally marked this red because we obtained a quite different picture after this major BW cloud maintenance. And it was quite a different and much better picture than before. So it was quite close to the local execution that we did. So then we decided also to increase or to test with different load levels. And we added medium and high, where for both we use chaos mesh to introduce some load into the cluster. And for the medium case, we use the configuration of 4 workers and 50% load, whereas for the high case, we use the load of 80%. And then we repeated the experiments. So we did additional runs. So now what you can see is that the blue part contains those experiments that were done before the cloud maintenance, whereas the red part contained those after. And the light red is about the medium load scenario. So I excluded the low load because it's quite similar. And the dark red is the high load scenario. So one conclusion here is that if you can observe in the high load scenario, finally the quality of service class made a difference, and it made a huge difference. And whereas for the medium case, it was not like not of a big significance. So to wrap up my talk, I have here some takeaways. So one is that, okay, we need to, it's also a general, like to expect high noise in performance measurements, and also to remeasure upon changes that you know that are either induced by you or by the underlying cloud provider. Quality of service classes matter sometimes, at least, because we saw before the cloud maintenance happened, they were not the most influential factor in our results. Another thing is that maybe we were just lucky in the new setup, and we were located with less noisy neighbors, for example. Which can be the case and deserves more investigation, but for that we need to have more knowledge as well. For our protocol library, I think that the most important message also for us is that it provides reliable load generation, and we can use it in this reference use case to make a use case also for other researchers, and then they would also obtain same performance characteristics. And in the future, besides investigating further the results we got, we also plan to see how now our predictions from the models of different scaling strategies, whether they can be treated as helpful in such uncertain environments. And with this, I would like to thank you for your attention and your time. And now I'm open for questions and discussions.
Thank you very much for the talk. I think the first question is by Murray Woodside. Murray, do you want to ask the question yourself in Zoom?
Sure. Actually, Florma, you sort of answered the question in your last slide. I was thinking that your users finally, I mean, the final deployment of the system is going to run up into the same sources of uncertainty as you have in your experiments. Mm-hmm. So you really need the uncertain environment as part of your analysis, but this is not a question about your load generation. It's a question really more about the use of the model and the way in which you make predictions. So I don't think I have much of a question. But what kind of a model? You're thinking in terms of a simulation model for the architects to use? Yeah.
Yes. Simulation model coupled with appropriate tools and DSLs so that he can model those scaling strategies.
But a simulation model that takes into account uncertainty is orders of magnitude longer to run than a simulation model that can count on a certain level of certainty. I mean, because you have to do the statistics. So it does make the model analysis, let's say, less lightweight. Anyway, thanks.
Thank you.
All right, we have time for maybe 2 more questions. I think then there's one by Lawrence.
Yeah, my question is exactly about this slide. What I noticed is that your execution times became much more stable. So performance variability dropped, but also the lower execution times that we see on the left are gone. What causes this? Is it just sheer luck that you were co-located with lesser noisy neighbors, or is there some overhead in becoming this stable in terms of performance?
I can't say for sure. I mean, as I introduced before, maybe that is also part of the answer here. Protocom does a calibration phase before we take measurements. So because the variability dropped, I think we improved also in those outliers. And maybe it's due to that. So my point is that it depends also at what time and in what state was the cluster when the calibration was executed.
Would it be interesting to take the snapshot of settings of Protocom from, let's say, the prior versions and then rerun it on the newer versions, in the red part?
Mm-hmm. Mm-hmm.
Okay, thanks.
Thank you.
Right, then let's do one more question while we switch the screen share. And I think there's a couple of questions from Alexandro.
Sure. Let's see with which one to ask. Yeah. So here is one. We seem to create lots of measurements and benchmarks that are trying to produce a single output from the system, let's say execution time. And we spend a lot of time trying to give a linear dependency of that output from one or several of the inputs. Are we doing the right thing here, given that these are very complex systems with a lot of variability we do not control? Are there better things we should do? How do we capture the complexity better than with a single value and linear regressions?
Is this a question for all or just for me?
It's for all, for everyone in the room, but since you're
I
you're
think
active right now, it's for you, but it's for everyone, clearly.
I think at least I hope I could make the message that our main goal is to test something else. So to test whether those prediction methods enable ranking design decisions correctly. And for this, we did not need to have like a very complex reference use case, but one that is more reproducible, and we can easier compare it to our models.
I would even argue that you captured a lot of unexpected complexity in the environment that runs it. So I'm wondering, how can we capture all those things somehow rather than keep measuring?
Mm-hmm.
Is there a quicker way, a smarter way, a way that doesn't require burning so many electricity watts and whatnot, watt hours and whatnot? Okay, it was a philosophical
that's
question.
a good question, but can't answer it.
Maybe some food for thought for all of us. All right, so let's think. Sorry, go ahead.
Let me say again, I agree with Florimond. It's not about only this work. It's about all our work, including the work I do and that others do, right? How do we reason about this? Okay, I'll stop here.
I got to be the bad timekeeper, and let's thank Florimond again for the interesting talk.
Thank you very much.
Could you stop your screen share so you can set up the next talk?
Is the screen visible?
Yes, this looks good.
Okay.
Feel free to get started because we're short on time.
Sure. Hello, everyone. I'm Trivikraman. So my fellow author Nikhil Ram and I will be taking on this presentation. So MyStrace is a framework developed by my fellow authors and I, and we belong to the Computer Science and Engineering Department of PS University, India. And before we get into what MyStrace is and what it does, I would like to give some background on what motivated the development of MyStrace. So most of the recent client-server web applications are adopting the microservice architectures due to their benefits like modularity and scalability over their monolith counterparts. And the highly networked microservice architecture brings in challenges of visibility into the underlying application. So by providing a deeper understanding into the functioning of the distributed applications, observability enables improving the performance of the system by obtaining a view of the bottlenecks in the implementation, and it aids in identifying the performance differentials. So MyStrace enables the required observability of the application through request tracing, that is, tracing the end-to-end path of requests through the application. So the visibility provided by the currently existing request tracers is limited to the user space and requires that the application be instrumented to track the request flows. Through MyStrace, we wanted observability at the kernel space, which allows monitoring of all activities in the request lifecycle, such as time spent in the network hops or the network stack, actual time spent in the CPU, page faults, and a variety of other events. Next slide, yeah. So this slide is an example of a trace obtained when tracing is limited to the user space. The end-to-end path of every request that enters the application is referred to as request trace, and every basic unit of work or basic operation that occurs within a request trace is known as a request span. Insights into the path taken by the request through different containers and the duration of the spans can be obtained from this trace. However, since it's user space tracing, insights into the activities going on in the kernel space cannot be obtained. Next slide. So MyStrace, which expands to microservice request trace, is an open source request tracer synonymous to frameworks such as Jaeger and Zipkin, along with the kernel space visibility provided by kernel tracers such as ftrace and bpftrace. Jaeger, Zipkin, and service meshes like Istio that perform request tracing require the application to be modified or instrumented in order to identify the trace to which a particular span belongs. This instrumentation is done through libraries such as the OpenTelemetry, which was previously known as the Open Tracing API. And this application modification is not required for the functioning of MyStrace. Moving on to the functionality. So MiserTrace initially identifies the request spans associated with the individual containers and then associates these spans with unique request traces. In order to stitch together the request spans into request traces without application instrumentation, or in other words, to isolate the path of the request through the application, MiserTrace tracks two categories of events. The first category monitored are the lightweight API calls that the containers use to communicate with one another. And these API calls are nothing but TCP network transfers in the eyes of the operating system. The other category is the asynchronous request handling in the microservice architectures. Suppose a container receives 5 simultaneous requests. In order to handle these requests, the container spawns 5 threads, and each thread handles one incoming request. So this is monitored by looking at the process forks and the process exits. Next slide. So in order to obtain kernel space visibility, MiserTrace supports two kernel tracers, BPFTrace and FTrace, that serve as tracing backends from which data is obtained. The users can enable any of the trace points and features provided by these kernel tracers. So FTrace is a tracer that is built into the Linux kernel and was first released in 2008. It initially supported only tracing of kernel functions and has since evolved to trace a variety of static events in the kernel. And BPFTrace is a high-level tracing language to the extended Berkeley packet filter that was introduced in 2018. It provides a high degree of programmability to the user and allows executing sandboxed code in the kernel. So MiserTrace associates the data or the events generated by these kernel tracers with the request spans that triggered the respective events. Next slide. So moving on to the workflow of MiserTrace. The first phase is the workload generation and the tracing phase, where the kernel trace logs are obtained. The second phase involves the processing of these captured logs from which the request spans and the traces are generated. And the last phase is the rendering phase, from where the request traces generated are converted to human readable formats. Now let's take a look at each of these phases in more detail. So the first phase involves workload generation and tracing of the containerized microservice application. And one of the important steps in this phase is to have the right trace specification. One of the required configurations is tracing only the processes that belong to the microservice application and not the entire system, so as to have lesser overheads and thereby have a greater accuracy during tracing. And the tracing backends such as FTrace and BPFTrace write to an in-memory ring buffer before the data is written to disk. So it is necessary to configure the right ring buffer sizes in order to avoid losing out on events during tracing. And in order to track the two event categories, that is the network transfers and the process forks, MiserTrace uses certain events provided by the kernel tracers. These events and also the events of the user's interest have to be specified in the trace configuration. And we have observed that tracing the kernel events required by MiserTrace results in a small overhead which manifests as a drop in request throughput by about 5 to 6%. Handing it over to Nikhil.
Looking into the second phase in the workflow, which we term as generation, here the request traces are identified for each request serviced during the tracing phase. This is performed by post-processing the trace logs generated by tracing backend. The time-ordered trace logs are streamed into this global object called as trace processor, which essentially consists of two stores, socket pool and application thread pool. These pools in turn store socket and thread instances, which are essential in simulating and storing the interactions between the actual network sockets and application threads that existed during the tracing phase. The thread instance is populated with request spans, which is handled by the corresponding thread, and these spans are tracked by the object called as thread state. Interaction between these thread states are interpreted through the thread state model, which I'll be explaining further. Once the request traces are isolated, the runtime global object trace processor is serialized and stored on disk to render to human readable format. Next slide. So looking at the thread state model. Thread state model is key to identify and determine the lifespan of each individual request span and to stitch them together to generate the request trace without instrumentation of the application. This also brings in identification of spans at the granularity of a thread instead of the service as a whole. For any interaction between thread, there exists a thread state object which maintains the start and end time of the span and is identified uniquely by trace ID and the source thread. The handling thread, which in case of a receiver thread due to a network interaction, or the child thread due to a fork, maintains the thread state and updates the span details as per the thread state model algorithm, which I'll be explaining. A reference is maintained from the parent or source thread to stitch together all these spans and construct a directed acyclic graph for the request. Next. So looking into the algorithm which we use, there are two situations broadly which must be handled: a process fork and a network transfer. Considering looking into the forks, consider here a scenario wherein the parent thread is handling 3 requests with trace IDs T1, T2, and T3. When the kernel trace point shed process fork is observed from the parent thread, the child thread instance is created in the thread pool store, and the trace IDs handled by the parent thread are propagated to the child thread to create a new fork thread, to create multiple new fork thread states, and the span is hence initialized. Further down the timeline, when the shed process exit event is observed from the child thread, indicating the thread is exiting, the fork thread state objects in the child thread are terminated, indicating the conclusion of the span. Moving on to network transfers. Let's consider a similar scenario wherein the source thread is handling 3 requests with trace IDs 1, 2, 3. Unlike a fork, the direct relationship between the source thread and destination cannot be interpreted, for which the network socket is essential as an intermediary layer. For this, we use the custom kernel probe event, which probes called TCP send, which probes into the sock send message and sys send message function in the kernel. So when we observe this particular kprobe event occurring in the syscall send context, which comprises of multiple syscalls like send to, send message, or write, we basically obtain the network socket object and update it with the reference to the source thread. On the other end, when we observe in the syscall receive context, which includes receive from, receive message, or read, and in this scenario, when we observe a trace point event, TCP receive space adjust, which basically indicates the copying of data from the kernel space to the user space, we obtain the network socket by referring to the parameters, and also find the relationship from the source thread to the receiver thread. And this, by identifying this relationship, we can hence propagate the traces from the source thread to the receiver thread and create new instances of network states and initialize the span. So moving on to the third phase, or the last phase, where we generate the request, generate a human readable format from the traces collected. We basically support 2 different formats, the directed acyclic graph format and the custom code execution format. So here we have a sample request trace generated by miser trace for a request when a workload was run on Death Star bench suite on a large core count single node setup. So Death Star Bench is an open source microservice benchmark suite consisting of multiple microservice applications. Here we see the source container Nginx at the top, wherein the request was received. We also see the start time when the request was received at the time, and the time spent in the span by the thread. And this is in nanoseconds. Further down the indents, we see how the request moved between threads and containers through forks and network hops. And these are indicated by the type of the thread state. As you can see, the network thread state and fork thread state. Moving on to custom code execution. So this is a feature wherein we enable user to add custom events to the trace configuration supported by the tracing backends, in this case ftrace and bpf trace. And we also support a few functions within miser trace to initialize data structures, process these data structures, and retrieve data once the trace logs are being processed. So moving on. Next slide. So here we have a brief pictorial representation wherein we enabled the events shed migrations and page fault user supported by BPF trace. And we added a counter code stub in the miser trace to count the following events for the corresponding request spans. And this output shows the number of the occurrences of these events for each request span for a given request.
So to conclude, MiserTrace is an open source framework that can trace requests to containerized microservice applications at the kernel space. And it is capable of monitoring uninstrumented or unmodified applications with minimal overheads. And it allows users to enable and track any of the approximately 50,000 plus events provided by the framework such as BPF trace and buckets them into the request spans in order to help identify and understand the performance differentials across different request traces. In this work, experiments were conducted on a large core count server. As part of the future work, MiserTrace can also be extended to support tracing of kernel activity on a cluster of machines to derive kernel insights irrespective of the scale of the application. And if anyone is interested, we can put in the GitHub link to this work on Slack, which people can look into.
All right, thank you for the quite interesting talk. I would like to start this off with a question from myself, actually. I'm very impressed with the amount of detailed and low-level information you're able to collect. Something I was wondering about is, as a user, how do I make use of this? Is this something I use to make performance optimization? Do I track down problems? So what are the use cases for me as the user?
Okay, so looking at it from a user's perspective, if say you're interested in looking at the network stack in more detail, you want to look at the time it takes for a packet to go from the transport layer to the data link layer, the actual time it spends on the physical link, the time it spends on the network stack of the receiver thread, and to look at all these from a request trace perspective and to compare these across multiple request traces. And this example of a network transfer I gave is just one of the many things that can be done, since we are enabling support for practically everything that's going on in the kernel. And another thing that has to be ensured is one should not enable, say, 1,000 events at a time, because that would indeed add to a lot of overhead during tracing. So something about 50 to 100 events, definitely we've observed that the overheads are less than 7 to 8% when, say, about 50 events are enabled. So that's one thing the user would have to take care of.
Okay, so quite interesting. The idea is to kind of give me very close to the hardware information that will help me track down what's going on. So I think there's another question by Murray, and after that we'll move to a quick break.
Yeah, I'd like to mention another use that can be made of this kind of extraction, because you can move from a model of spans directly to a performance model at quite a high analytic level if you want to. And we have, this work is, this business of extracting the beginning and ending of spans is rather similar to some work we did called architecture extraction, SAME, S-A-M-E, 20 years ago. But we assumed we had the message from end to end. We were just looking at message-based spans and getting the message. We tried getting the message out of kernel traces using a different kernel tracing approach, and we found it very challenging to correlate the beginning of a message and the end of the message at the level of application to application messaging rather than packet to packet. So I congratulate you on getting that done, but I think that there's quite a lot can be done in terms of, say, bottleneck detection and things like that, bottleneck prediction.
Thank you for those insights. We'll definitely take a look at your work as well, and definitely it does open up avenues for a lot of kernel
I'd be happy to communicate about all this. I'm very interested.
Sure, yeah.
Thanks a lot.
Yeah, our tool basically opens up the entire kernel for your use. So any event which you want to track within the kernel, which is supported by ftrace or bpftrace, it could be anything. It could be memory, it could be network, it could be buffers, it could be IO, it could be anything which is observable through the kernel. You can use this to tag any such performance with a microservice request.
Right,
One
so
more
there's-
thing
yeah,
I
go for
would
it.
like to add is we currently support network hops and forks. So there could be more templates added which could support other interactions, and that could be separated out as a different state. And that could be looked into further detail lower down.
All right, so there's quite a few more questions in the Slack that you could answer there, but so we can stick to our program. I would suggest that we now take a quick 3-minute break and then start back out with the next keynote. And let's thank the authors again for this pretty interesting talk.
Thank you.
And while everyone else is taking a break, I will ask Lydia. Hi, hello. Yes, I can see you.
Hi, Alex.
That's good. I will ask you if you can see and, well, test whether the slide sharing works.
Let me see. Yeah.
And in the meantime, I see that, I see, yes,
Is
this works perfectly.
Is the rice slice?
I don't know, I'm seeing tuning ImageNet.
Okay, then that is not so bad.
Okay, then it looks like we're seeing the right things.
Yeah, because sorry, I have to.
And I see also Robert and Lawrence. Okay, just that we know that everyone is here. What I will do during the session is to try to somehow indicate that there are 5 minutes left. I don't know if it's possible to see this, so I will try to just show 5, but I don't know if it's possible for everyone to see when you're in the heat of the action, and also with Zoom showing or not showing things. But I would like to ask you to tell me now if you want me to stop you when there are 2 minutes left in your time slot, because that would give time for at least a question. If not, I would just let the clock run. Just let me know what you want, what you prefer.
I have a big clock in front of
me. Well, okay.
Yeah. So 2 minutes, right? No, I got it.
Okay. And Robert, Lawrence, same comments?
I'm not sure. I also will use a timer, so I will see how much time I've spent.
Okay, so you do not want me to stop when there are 2 more minutes, because that's fine. I do not insist on stopping anyone. I would prefer not to stop anyone, but okay. Then let's give it 30 more seconds for everyone to return, and then we can get started.
It's a beautiful day today.
It is indeed.
Yes.
It actually, right? It depends where you are, right? Because we have
in Delft, we have good weather. I thought that we are on the same boat.
It's a problem, right?
No. It's a problem to stay at work. That's the problem.
There we go. Okay. So welcome everyone. Welcome back. It is my great pleasure to introduce Lydia Chen. She is currently an associate professor at TU Delft. She worked for a decade at IBM Research, the Zurich lab. She's leading the distributed learning systems lab, and that is exactly what triggered us to ask for the keynote, because she's a specialist not only on actual performance modeling and improvements, but also on all the different parts that appear in this title of Distributed Learning Systems Lab, in big data systems, in learning, or in particular deep machine learning, and more recently also on privacy enhancing technology. There is also a very nice startup that you might want to mention, we'll see. So Lydia has a lot of important knowledge, and it would be great if she can share some with us. Without further ado, please go ahead.
Thank you, Alex, for your very nice introduction. I don't know if I can speak so nicely about myself. So good afternoon, good morning, everybody. So I'm going to talk about efficient system and hyperparameter tuning for deep models. Let's see. So artificial intelligence and deep neural networks are in our life. You probably have read the news from the headline news that AI robots can beat the lawyers in NDA readings. AI is driving the cars on our behalf. What are those AI models? So I don't know, somehow my slides is a bit messed up here. I hope it's fine. I tested a lot. So deep neural network models, many of you might know already, right? So it's basically organized by different layers. Each layer has many neurons, and they are usually in the order of several millions. In order to figure out the weight of these 1 million of neurons, we need to go through training. That's where we thought it takes a lot of time. But in reality, that's something called hyperparameters that control over these models. What are those hyperparameters? These hyperparameters set number of layers, set number of neurons. When we have these new set of parameters, we got new models. We have to train again, again, again. And in addition to these network models, network hyperparameters, we also have these so-called training hyperparameters. So it decides the learning rate and batch sizes. That decides how this training algorithm is going to use the data and updates the results over different iterations. So I want to use this slide to say that to get good model accuracy, it's not just about model training, it's about model tuning. Tune the hyperparameters and then train the models so that we can get the accuracy that the AI can drive the car for us. So actually, I have to say one thing. These slides, I think I have this is a problem of my slides. Maybe this is the wrong set of slides.
Okay, let's
interrupt
and
actually, can I interrupt a while? Sorry, sorry
no
about that.
Exactly. Just let's stop for a second and then we restart. Not a problem. This also allows me to take again a snapshot of the first slide, because that then I can place it on LinkedIn or something to advertise it. I missed it.
Sorry about that. I just realized too many versions of the slides. So let's go back a little bit, right? I was talking about hyperparameters are very important. So well, we essentially, in reality, we are not just doing training, we're doing hyperparameter tuning. Is that really so bad? Let's look at a very extreme case, tuning ImageNet. ImageNet is one of the most difficult data benchmarks for deep learning folks. It covers 1,000 classes, more than 1 million images, and published by OpenAI. And it tries out the different neural network models, right? It's a tuning process, but it's a bit more elaborate. To reach certain accuracy, you can see how much teraflops per second per day is needed, right? So the legend is AlexNet, GoogleNet. You can think about just a different kind of model. You can think about different kind of models we need to tune. So it's very daunting. It's what really consumes a lot of computational power. way more than training. And it's very, very, very important. A quote from Turing Award winner, 2018, hyperparameters are like cockroaches. They are everywhere. You cannot avoid that if you want to get good performance. So let's look at a smaller example. We are academics, right? We don't need to tune big model like ImageNet all the time. Let's look at LabNet, a very small model to classify in this data set, handwritten digit on the top corner. It wants to recognize, it asks the model to recognize 1, 2, 1, 2, 3, 4, up to 9. So it's very small models, right? But let's see, if I change the number of parameters I need to tune, network size, to the learning and learning rate and batch sizes. And you can see the training time and the cost on EC to ML optimized instance grow exponentially with respect to number of parameters. Why? Because when you train one hyperparameters, you just need to try a few range of that particular hyperparameter, say batch sizes. But when you have to train 6 parameters, you have to try all the combinations of all the ranges. For such a small model, classroom model, right? Classroom example, it costs you 80 euros already. Small example, very expensive. Let's zoom into what this really means, right? Small example, we say let's tune the batch size, usually the most critical variables. This batch size, default people set 32, means that we send in 32 images to this iterative stochastic gradient algorithm to solve, to figure out the optimal model weights. And we can do it with 64, 256, 1002. This is the typical hyperparameter. No doubt it has impact on accuracy, but our small experiment tells us it impacts the training time as well as the energy, the amount of energy you need to spend on the tune. Again, surprisingly high. So this hyperparameter actually impacts the system performance. So this is an example done by single core. What if I now change it to the multiple cores? I can do tuning on 1 core, 2 core, parallelize that. Will I get a better performance out of that? Will I be more efficient? So on the right hand is the training duration, basically training time, normalized against the single core left-hand side result. But you can see, don't read the value, but what I want to tell the message is the impact of this batch size hyperparameter actually differs, depends on how the system parameter, core is really a typical system parameter, how they interact with each other, right? So through this small example, we're going to say tuning is expensive, and hyperparameter tuning and system parameter tuning interact with each other. So another example, ResNet, a bigger model than LabNet, published in 2015. I just want to tune the learning rate and batch sizes. That's what a lot of learning people do. But learning job sit on top of Spark. Spark has executor to tune. I think everybody here knows very well, right? You have to decide number of cores and memory. And you usually put Spark on top of Kubernetes. Again, what's the number of core? What's the memory? You can do default setting, but we say we don't do default setting. What we do is that for different kind of model, this is on the data of CIFAR 10, we just say, let's deviate from the default value. Let's do 1 core on the driver, 2 cores on the, 1 core on the driver of Kubernetes, 1 core, 2 cores on the executor. We just change the value. What I want to highlight this, we deviate from the default value. You can see for both of the model, we got CPU reductions and the memory reductions. We are much lower than what the default value says, but this example actually can achieve the same accuracy. So system parameters need to be tuned. We are running our deep models on a huge system stack. We cannot just tune hyperparameter. We need to do both at the same time. In the system, the cluster, the jobs comes in a dynamic way, right? That's further complicated. Should I make the system parameter fixed, or should I dynamically change that? So research questions I would like to address here is, could we find a way to jointly tune the system and hyperparameters together so that the model accuracy is maximized and the tuning time, the amount of resources tuning needed are minimized? By the way, state of art tend to answer these two questions separate. I think the people here, we know the system parameter tuning, we have been doing that to optimize the performance. But actually, we can actually do together, two birds in one stone. So here is what I'm advocating here. Tune these two types of parameters together, let's collaborate. The challenge is system parameters is already so difficult to tune. Now we have hyperparameters. The time and the cost grow exponentially. Is there really a way to do that? We have experimented some solutions of that. We think that it's possible. Over the years, together with my collaborators and my own team, we have tried pipe tune, multi-tune, H-tune to solve these research questions. I wouldn't say we solve all, at least some on whole. So pipe tune is published in 2020 middleware. So let's say, go back to the question. We want to tune hyperparameter system parameter together. Then we say, what's the naive solutions? We can simply apply the existing solution. The state of art is tune library from Berkeley, and it provides a lot of hyperparameter tuning algorithm, BOHB, you name it, hyperband. We just apply that, right? So I would like to make a note. State of art of this tuning algorithm is based on multi-fidelity. What it says is that instead of doing regular training from typically people would do train them given a set of parameter. I train from epoch 1 to the epoch 0. Epoch 1 to epoch 100. But this tuning algorithm says, no, don't do that. Just train a small snippet of the algorithm, maybe a few epochs. And how do I choose which trial to do? It's guided by random or grid search or Bayesian optimizations. So I hope that much you know. The tuning algorithm basically try a small trial. And then this algorithm, so if we can apply them, well, we essentially just treat system as one of the hyperparameters. And we change the objective function. So typically, hyperparameter, we say we maximize the accuracy. Now we put the system thought into that. Let's maximize the accuracy divided by the training time. Ooh, we solved the question. The only problem is it's very, very, very slow, right? If you have to do things on the fly, you cannot really afford this. The more time you spend on tuning, the more the costly it will be, right? We are academics. We don't have all this server lying around and free of charge, like Google. So what are the opportunities for us in these, for us to do it, to accelerate this, to reduce the time, right? That still achieve the goal of tuning these two types of parameters. There is stochastic gradient descent. It's an iterative algorithm. It goes to the data in multiple epochs through the forward and backward pass. Okay, if you look at the resource counters, here's an example of 56 resource counters over different epochs. And the color represents the values. You can see the values stay very constant. That means that after the epoch 1, you pretty much know what will happen in terms of resource demand for epoch 2, epoch 3, and 4. So the opportunity for us to accelerate this tuning process is the repetitive resource patterns. And our idea is, that's fingerprint the resource pattern to help us to train at least the resource pattern part. So this is the whole idea of pipe tune. So I can only give the high level pipe tune. Pipe tune basically train the hyperparameter job in the following way. consists of models, consists of data sets, and consists of a set of hyperparameters and ranges. Not just hyperparameter, but its ranges. And it separates this hyperparameter in two ways. Typical hyperparameter related to the models. What the models people think about hyperparameters. We have a tuning algorithm, and the objective is to minimize the error. And then it knows that at the same time, it's minimized the training and tuning time, because we want to minimize the cost to do it. That is system parameter parts. So essentially, you can think about it has to turn two knobs at the same time, and finding the best combination of these two knobs, two types of knobs. And for the hyperparameter, it goes through multiple epochs, so it's very slow. For the system parameter part, I already told you, it can be quite fast because it doesn't have to go through multiple epochs, like what people usually think. To tune the system hyperparameter for this type of algorithm, one epoch, the reference epoch, is already good enough. Okay, so having this in mind, let's accelerate the system parameter search. So the pipe tune doesn't really touch the hyperparameter part. The novelty pipe tune really comes from combining hyperparameter tuning and system parameter tuning at the same time. And the second novelty is that's accelerate the system parameters tuning through the resource fingerprinting. How do we do that? So let's memorize the resource pattern of tuning job. For any tuning jobs, right, that characterized by models and the hyperparameter set and ranges, let's remember their reference pattern after epoch one. They say that's our reference epoch. And for each of the job we have seen, we remember that reference epoch. And whenever a new tuning job comes, we need to tune model and system parameters. Let's see if we can match any of the execution to already what we have known. So we do have system similarity classifications or clustering based on this so-called reference epoch. If we can remember what have happened in the past, then we can immediately do a table lookup. So due to the interest of time, I just want to tell you what we did here is we use GC Forest. It's a forest-based model, but it has the features of deep learning, multi-layers. So it can transform, it's a very nice feature representations. So once you are able to classify any new coming work, map to the existing one, and you can just say, based on the previous work with that resource application, what's the optimal system parameters? So that accelerates the system search furthermore. Here's the evaluations of our single tuning job. Here we can see, we compare pipe tune with tune V1 and tune V2. Tune V1 essentially is tuning without system in mind, purely deep model focus. Tune V2 is like the naive solution I present. So you can see how the pipe tune is able to reach the maximum accuracy over the wall clock time of the tuning. Tune V1 trails second, tune V2 because it's trying to tune all the parameters at the same time. It's extremely slow, no surprise. But at the same time, I want to show you that pipe tune is able to reduce the tuning time per trial. So because pipe tune has two objectives, accuracy and the tuning resources. Basically, time is a sort of resources. And here you can see that over the work clock time, pipe tune is able to find the instances that minimize system configuration that can minimize the training trial time. And tune V2, since it has this objective, it can do the same thing. But in contrast to tune V1, which is completely system oblivious, cannot do any of that. So Let's look into a bit more complicated example where the system, where the tuning jobs comes over the time. Okay, so, and we are able to do that quite well. We consider two types of workload: type 1, image-based; type 2, text-based tuning workloads. Those are the dominant deep learning model, images and text. Again, we compare tune v1 and tune v2. In this example, I would like to highlight, even in a dynamic kind of workload, we are able to achieve lower average response time of tuning jobs. So those are like, we set up a tuning cluster, jobs come in over the time, and we need to tune, we need to find optimal parameters, we need to find for each of these models. So we're quite happy with how PipeTune is able to learn this optimal setting on the fly. So we continue to the multi-tune. I'm not going to into the details of multi-tune because the time I lost at the beginning. So the multi-tune idea is what I have shown you in the HTune. PipeTune, it's a still single objective function. We massage the objective function to sneak in the system parameters. But let's give a bit higher priority to system parameters. We really would like to explicitly minimize the resources used in different layers of the systems, minimize the core consumption, RAM consumptions. And what here in the multi-tune is we explicitly model those objective functions through multi-objective Bayesian optimization. Multi-objective functions, essentially, I would like not to go through this. I would like to stress that multi-objective functions tuning, it's even more time consuming than the single objective, not too surprised. The more objective function we need to deal with, and the tuning cost will be even higher. So due to the interest of time, I cannot really show what I can do here. Sorry about that. So I would like to skip all of that. Unfortunately, if you're interested in that, you can get the paper from me. I will be happy to share the result with you. So a highlight of this is that we are able to go from PipeTune to a more complicated model, AlexNet. If you know, it's definitely much more complicated. And we are able to show that even though we tune much more, we have much more complicated objective function and hyperparameter space, we're able to achieve the accuracy. And then resource savings, and we are able to also reduce the searching time. So you might say, why do I hurry so much? Because I'm done, right? These two work shows that I sort of address the research problems, achieve the high accuracy, reduce the resource saving. I'm done. Why do I have to do more, right? Why do I have to, what I'm going to talk in the rest of 3 minutes? So I would like to use this chance to highlight what we didn't do well enough. So when you do all these models, why do we do these models? So that the end users like us can use it on our daily life, can use on the driving car. So we are talking about inference. All these models is to set up such that inference performance is optimized. You can use on your cell phone, you can use on your camera. So to optimize the inference experience. But today, the inference is done completely different from model training and tuning. We train a lot of, model provider train a lot of models and put it there. Say, here are the trained models. Facebook says it has 1,000 models just for object detections. Users, you try to figure out which one matches you. All the other guys say, small company, I can only train you 1 model. Choose whatever, choose this model or you leave. But users run their models, have very different inference requirements. They have energy consumption on their devices. They have good weather and bad weather. So what I didn't say in the first part of my talk is we train so much, we tune so much, we might produce a lot of model that's of no use to anybody. So I think the focus of tuning and training should be on the inference part. We should tune the model such that user can have a great model to use. That's where I want to turn the this whole talk toward at the end. So can we do that? Yeah, you can. Solution one, you directly tune the model with your inference in mind. We already have the paper. It's will appear in middleware. What it says that that's tune with objective explicitly to minimize the energy consumption of inference devices. And our algorithm is called one-fold tuning. There's another solution we have tried. It's called Lego DNN. So what Lego DNN is actually an online inference-aware tuning algorithm. When we receive a request from the user, say, I want the DNN model to do object detections, we immediately assemble a model, tune a model, and provide a model weights. This is possible through an idea called block grain scaling. Taking the idea from Lego. Lego, you can assemble the Lego by small pieces or assemble them through blocks. If you have to build the Lego from small pieces, it takes a lot of time. But if you are able to modularize Lego in blocks, you will be able to assemble the big Lego house in no time. That's how we see its analogy to DNN training online in an online way. We try to dice the neural network, ResNet, as shown in the example, through blocks. So there are challenges, right? The challenge here is, how do we find the blocks? And how do we make sure blocks can be assembled, like Lego can be assembled, they have a standardized interface? And how do we know which one to assemble such the inference objectives, like the minimize the energy and accuracy can still be met? So those are the questions we addressed in this paper. We just presented last week and MobiConf 2021. Yes, I rushed a little bit. I think that what I say is, so far, tuning job is really the heavy one, much more than the training. We start from model focus of tuning. Now we open up to model the system because we know tuning takes a lot of time and energy. I think the next level is we should tune such that users get the best models. Users' energy on their devices is minimized. So with that, I would like to conclude my talk and open the floor to everybody. Like questions.
Thanks for the keynote. So applause. Let's thank the speaker. Let's take one or two questions. I think Simon did not get the chance until now to ask a question. So Simon.
All right, so I'm quite fascinated by this approach of using the resource profile of a single configuration that you see and to kind of map this to other executions you've seen previously in order to save time for the optimization. I'm wondering if this is applicable just in this domain or if you think this might be transferable. And if so, what would properties of a system need to be for this to be transferable to?
This resource fingerprinting is done on the same hardware. So we basically all assets of hardware. We take the perspective of the training provider of the training cluster, provider of tuning clusters, so that the system profile is in a way controlled by us, controlled by them. So that's why the fingerprinting possible. We sort of remove the system heterogeneity out of the picture. So bit cheating in a way, you can say that, that's possible. I think that you point out something very interesting and very promising is this model should be transferable from different kinds of devices. So I think that based on our experience that you can basically train a big models, the base models, and you basically split according to different kind of system hardware, system specs. So like say you have Intel-based systems versus you have AMD-based systems. So I think that is doable. And then I saw a work that GC Forest and making GC Forest transferable. So that is very indeed possible and very promising area.
Thanks.
Okay, let's take the last question from Lawrence. There are more in the Slack channel, Lydia, if you want to go in and type things in. And also you can share your slides if you want to, so then others can see them and continue to interact with them and then send you messages and whatnot. So Lawrence, please ask your question. I will ask also Lydia to stop sharing her screen. And while Lydia is answering, Lawrence, you might want to prepare your presentation. Okay, so please ask
I'll try to do both. I'll first ask my question. So first, thanks for the interesting talk. So what I was wondering is, you mentioned that instead of running multiple epochs, you just run a single epoch to see what happens. You also mentioned a sort of portfolio of, let's say, different models. My question is, can you somehow run a single epoch in parallel using different configurations and then perhaps speed up your model training even further? So going back to your formula of accuracy divided by time, that you reduce the time by exploring different things in parallel. Would that work?
Yes, in parallel. So this is so basically probably, I don't know if you can see, you can tune the system much faster, so you can tune in parallel. But if we consider the time, you can accelerate, right? But if you look at the absolute computational time, the number of server you need to run that at the end is the same. So parallelism doesn't fundamentally solve the computational time we need to pay. It solves the wall clock problem by parallelism, but the computational time, if we need to pay by flops per pay by number of flops we use, then it's the same.
Right. Okay. So the money would be the same, but would you get your results faster? Wouldn't that be a benefit? So your model is faster ready?
Yeah, that can be benefits.
Okay. All right. Well, thanks for clarifying that.
All right. Then let's thank again the speaker. So many thanks, Lydia. I hope you have access to the Slack channel.
I will try. So far I have a little bit problem, and yeah.
Okay, then we can fix this offline. I'll be happy to help, or we can fix this over email so that you do get access, because there's a lot of nice conversation there, and you also get access to all the slides and comments of everyone. So that helps.
Thank you.
Okay, then yeah, I think here I should pass the microphone to Simon.
Right. So our next talk is task flow and energy and makespan aware task placement policy for workflow scheduling through delay management by Lawrence Velsius and Alexandru Yusuf.
All right. Thank you very much for that introduction. So that allows me to save some time by skipping the intro slide. So let's get straight to it. So in this talk, I'd like to combine three different topics. The first one relates to energy and makespan awareness, so metrics. Then the second one is task placement policies and workflow scheduling. And the third topic is delay management. Now, next to this talk, I hope that these topics inspire the community to also further explore this direction and also to find usages for the idea that is underlying. So let's get started. So many aspects of data centers nowadays are growing, their sizes, their usage, their revenue, but therefore also their impact on societies and economies. So within data centers, there are several metrics that are deemed important for both customers and providers, and two are quite common. The first one is costs, and the second one is performance, kind of the keynote that we had today as well. So when it comes to costs, energy has a direct impact in costs. And I am sure that most of you are familiar with the graph currently on the slide. This is the price per kilowatt hours that you have to pay currently in the Netherlands throughout the years. And as you can see, the price has skyrocketed due to both COVID and the war in Ukraine. So data centers, of course, face similar issues. Next, energy is a direct impact on our climate, or has a direct impact on our climate. This figure you can find in our article. I won't go into details, but one of the things that you can get from this figure is that in 2017, 1.4% of all power was consumed by data centers, and this already rose to 2.3 in 2019, which is quite a lot. So then there has been an increased scrutiny from governments because of this. So very recently, a hyperscale data center from Facebook had to cancel their plans due to political pushback. It turned out that their hyperscale data center would consume the subsidized energy equal to all the amount of energy consumed by this hyperscale data center would be equal to the subsidized green energy of projects right now becoming available, which led to this political pushback. So this means that also public image is becoming increasingly important when it comes to energy for both governments and companies. So the second topic of this talk is workflow scheduling. So workflows are one of the most common job types. We adhere to the model of Kaufman and Graham, which models workflows as directed acyclic graphs, or DAGs. So an example is shown here on the right-hand slide. So in workflows, tasks are modeled as vertices, and the dependencies between tasks are modeled using the edges. One important property of a workflow is its critical path. In this case, we marked it red. And the critical path is basically the chain or chains of tasks that form the dominant runtime of a workflow. Now, tasks are the most granular element that should be scheduled. And this means that we can pick the location, in other words, the machine, where these tasks will be executed. And this is done via a task placement policy. And that brings us to delay management. So we noticed that some tasks have leeway. In other words, we can delay them without impacting the path of the critical path of the workflow. So if you take our previous example and assume that all tasks arrive at an equal time, then you notice that both task 1 and task 2 have as parent task 3. But because task 2 has a runtime of 15 time units, task 3 cannot start before 15 time units have passed. Since task 1 only has a runtime of 10 time units, this means that there's a delay possible for task 1 of 5, and we call this room for delay slack. Now, in our article, we introduce an algorithm that can compute these the slack of all tasks in a workflow in O, V plus E time and space, where V is the set of edges and E is the set of vertices and E is the set of edges. And this algorithm forms a good alternative for the algorithm of Lee et al. Their algorithm has a runtime of O V squared. The core of our algorithm is based on topological sorting. That's where the main runtime comes from, but this is single-threaded. And this runtime can be reduced via parallel and therefore distributed computing. So there is some room for improvement left there. For details on our algorithm, I refer you to our article. So the next question is, okay, so how much slack is there actually in realistic workloads? So we took the traces from the workflow trace archive and we split them by domain. Now, please don't try to read the numbers. All I want to say here is that we found that all domains contain slack. And that brings us to the topic of this paper. So we asked ourselves the question, how can we exploit slack to reduce power consumption? And we came up with two ideas. The first one is to exploit heterogeneity. That means that we try to run tasks on slower yet more power efficient hardware. So in this table, we outline some very recent CPU models, and we list the base clock speed, the amount of logical cores, and the TDP. And if you look at the amount of watt you have to spend per gigahertz per core, then you see that there are that these vary up to almost 3 times between these CPU models. The second idea that we had is to delay tasks on a machine using DVFS, dynamic voltage and frequency scaling. We didn't have a DVFS system, so we took the numbers reported by Dieman et al. And we averaged their single and multi-threaded workloads. And we obtained the table below. So we used these two tables to perform first a first check with rough numbers. So we made the following assumptions. First, we inspected each workflow independently. Second, we assumed that the task runtimes are based on the fastest machine of the table that I just showed in terms of clock speed. We also assumed that the runtimes scale linearly in clock speed and that the machines support DVFS per core. Now, of course, this isn't realistic because workflows in a real system would run in parallel, influence each other, and the other assumptions would generally not hold. But this was purely an exercise to check if this idea was viable and to basically get a feeling if this idea would work at all. So the results, we investigated 3 different approaches. The first one by just checking the impact of exploiting heterogeneity. And there we compared the fastest versus the most powerful, power efficient system. Then we inspected the impact of just DVFS and then the combination. For the sake of time, I'll just present the energy reduction results of the third configuration. Please refer to our article for the others. We saw that for the scientific workflows, we could get an energy reduction on paper of 18%, for engineering 32%, and for industrial 47%. And of course, take these with a grain of salt. But now that we know that our idea could work, we decided to implement the idea in a task placement policy, and we call it task flow. So task flow selects tasks in a first come, first served manner. It performs backfilling. In other words, it loops through the queue in case the task at the head of the queue doesn't fit. And it does this until there are not enough resources left for any task to be scheduled. And it attempts to delay tasks by exploiting heterogeneity and optionally DVFS within a slack bound. And by doing so, we aim to avoid impacting the make span of the workflow. And hopefully this improves the adaptability of a policy. So if a workflow wouldn't cause delays on other workflows, we hope that it provides less of a risk to be adopted in real systems. We used simulation to investigate the cascading effects of delaying tasks and therefore making our results more realistic. But simulation also allows us to process large workloads in little time using very few resources. So for simulation, we used a modified version of OpenDC, which is open source, also linked in the article, and the workflow traces from the workflow trace archive were used. We made similar assumptions as in our rough number section. I refer you to our article for all the details there. And next to task flow, we also implemented a throughput-oriented task placement policy that just picks tasks also first come, first serve, but puts them on the fastest resource currently available and doesn't apply DVFS because that would slow down things. And we made this policy the baseline. So the results are as follows. In the top figure, we list per domain the total energy consumed in kilowatt hours. And vertically, we list the baseline at the bottom, then the option of task flow, just exploiting heterogeneity. And in the top, exploiting heterogeneity plus DVFS. And in the bottom, we list the same, but then just horizontally, the cumulative job delay that the cumulative job delay that was incurred throughout the execution. So if we look at the first domain, the red bars, which is engineering, then we note that we can get, compared to the baseline, an energy reduction of 3.8 and 4.2% respectively, at the cost of an additional job delay of 0.1% and 0.7. Now, if you look all the way on the right, the green bars for the scientific domain, leaving the industrial as last, then we see an energy reduction of 0.1% and 0.9% respectively, at the cost of minus 0.6 cumulative job delay. So we actually reduced the job delay in the system a little bit. And for the heterogeneity plus DVFS, we saw an increase of 0.1%. Now, the industrial traces showed quite a different story. There we obtained an energy reduction of minus 10% and minus 13.6% at the cost of 16.4 and 98.7% in job delay, respectively. So we dug into why this happened. And it turned out that our task placement policy was starving large jobs in the industrial trace of resources. So this caused these large tasks to only be executed at the very end of our simulation, which caused the increase in cumulative job delay. So our careful conclusion is that using Slack to reduce power consumption looks worth following up, but we need a way to deal with this task starvation. So that brings me to future work. We would like to see how TaskFlow would behave on a real system, and also compare it with state-of-the-art approaches. Perhaps it can even be combined with a state-of-the-art approach. Next, we hope that the community finds novel ways to exploit the underlying idea, the idea of finding and using Slack somehow. We have some ideas there. Hopefully one of you is interested in this topic and willing to look into it. For example, mitigating stragglers by running speculative copies of tasks in these Slack gaps. Reducing deadline violations by scheduling tasks in these Slack gaps. After all, not all delays can be seen, for example, hardware failure. Improving task flow by using an anti-starvation approach, or something like a brokering approach where you can trade your Slack for perhaps some benefit or financial benefits. So I'd like to end this talk with reaching out that if you think these topics are interesting, then do reach out to us, to the at-large research group, because we're always happy to collaborate. And with that, I'd like to thank you for your attention, and I'm happy to take any questions right now.
All right, thank you very much for the interesting talk. So let me start this off with a question about how you calculate the Slack. I've probably missed this, but do you calculate the Slack based on when the job ends versus when it's supposed to end, or is it a latest start date?
So how we compute Slack is for each task, we look at all its parents and combine, first of all, we look at the arrival times. So traces, they list them, but there are also for online approaches ways to make educated guesses when things come in and how long they take in terms of runtime. But what we do is we look at the task runtime and then also at the parent to when it's supposed to start and its children respectively. So then we can compute for its parent what is the time that this task should be starting, which is kind of the maximum between the arrival time and let's say the time of all its children that will finish. And if there is a difference between the time that the child will finish versus when the parent is supposed to be starting, that's how we compute the Slack. I hope that makes sense.
Yeah, what I'm wondering is basically, do you need Oracle style information to calculate the Slack, or because it's nice to know that we have Slack after it happened,
yes,
but in practice we would need to know about the Slack beforehand, right?
Yeah, we addressed this concern also in an article. So job runtimes need to be known, or at least you need to have some kind of guess there. There are systems that can quite accurately guess runtimes based on prior executions and, for example, cron jobs, they're very predictable. Task structures are typically known beforehand by systems such as Spark. There it already computes the entire DAG. So there you can assume that these things are there. If they're not, there are ways that if you only have partial information, for example, if you have a group of, let's say, children tasks and already its parent known, then you can, for that piece of the workflow, do the computation, but not for the remainder if that's unknown. So there are some methods there where you can already derive some information, but not everything.
Right, this is pretty interesting. In the sake of time, let's move the discussion to the Slack. And could I ask the next speaker to start sharing?
Yeah.
Let me try to see why Slack won't pop up in its fullest form. There you go. Sorry about that.
No problem. Okay. Can you guys see my screen and everything? Are we all good? Okay. Hello, my name is Robert Cordingley, and today I will be presenting Facet, the Function as a Service Experiment Toolkit, a Jupyter notebook to streamline every facet of serverless development. This presentation will be organized into 5 main sections: the introduction, our supporting tools, a deep dive into the Facet workflow, an evaluation of Facet as an experiment client, and finally, our conclusions. So we'll go into the introduction. Serverless function as a service is a relatively new cloud computing delivery model where developers write their applications as individual microservices that are automatically scaled and hosted by the cloud provider. Fast platforms offer a number of appealing features, such as no infrastructure management, automatic scaling to meet changing application demand, and fine-grained billing models based on actual usage of your application. While there are great benefits to using fast platforms, they present unique challenges when it comes to packaging, deploying, testing, and running experiments on them. For example, cloud providers tend to lock developers into using their specific platform and services. Vendor lock-in makes it more difficult to deploy applications across multiple fast platforms to do comparisons, tests, and experiments. For example, let's take a look at all of the tools and services you need to use for multiple fast platforms. Let's say we want to deploy a function to AWS Lambda. In the simplest case, you would use any text editor to write your code. You would package it as a zip and upload it to the cloud using the AWS CLI. If we want to package our function as a Docker container, you would have to use Docker and AWS ECR to host your Docker container. And then if you want to do all those same things with Google Cloud Functions, you would have to use even more services like the Google CLI, along with BuildPack to build your containers, and your functions would be running under Cloud Run. If we wanted to expand to another fast platform like IBM Cloud Functions, you would have to host your Docker containers using Docker Hub, and your functions would be running using Apache OpenWhisk. If you wanted to use Azure Cloud Functions, they would really want you to use their VS Code plugin, but every platform has their own command line tools that you'll have to use. If you wanted to run experiments, you may have to use data analysis tools like Jupyter Notebooks or RStudio. And let's not forget about open source fast platforms like OpenFast. Then you'll need to host the whole platform yourself using Kubernetes, OpenShift, and any cloud Kubernetes service that you want to use, all compounding on the number of tools that you'll have to use. To simplify this whole workflow, we created the Function as a Service Experiment Toolkit, which integrates with Jupyter Notebooks to provide a streamlined workspace. Next, we'll talk about the supporting tools we've created over the years. To complement the Facet notebook, we have created 2 other tools: the Serverless Application Analytics Framework, aka SAF, and Fast Runner. SAF is a profiling framework written in multiple languages, including Python, Java, Node.js, and Bash, and is included in the deployment of fast functions. With only a few lines of code, SAF can collect important resource utilization metrics, information about the host infrastructure, and details about the fast platform to enable performance and cost characterizations. Fast Runner, on the other hand, is a Python client application that can invoke batches of fast function calls to run experiments. Fast Runner has dozens of parameters to define how experiments are executed and orchestrated, and then compiles the results into accessible reports. Next, we'll move on to a demo of using the Facet framework and how it works. At the core of the Function as a Service Experiment Toolkit, it is a Python library that automates function creation, development, deployment, testing, and integrates well with Jupyter Notebooks to provide an accessible workspace for fast development and experimentation. Facet supports writing and deploying functions to many different fast platforms with multiple options for configurations. Facet can deploy to AWS Lambda with both Intel and ARM Graviton architectures. It can build functions as zip files or Docker containers, allowing development of functions with complex dependencies. It can deploy functions to both generations of Google Cloud Functions, IBM Cloud Functions, which uses OpenWhisk as the fast platform, Azure Cloud Functions, and finally, self-hosted OpenFast deployments. This figure shows the entire workflow of using Facet, and we'll break it down into 3 key phases: the development, deployment, and testing phase, experimentation, and then finally data processing and visualization. To start, we'll go into the development phase. So let's create a fast function using Facet. Here we have a basic hello world function formatted how fast platforms usually work, where functions take a request object and return a JSON object response. This function is simply responding to the request by saying hello to whatever name is provided. So to deploy this function to AWS Lambda, all we need to do is import the Facet library and then add the Cloud Function Decorator that defines the platform we are deploying to, in this case, AWS Lambda, and then a configuration object that defines additional parameters that our function may need. In this example, we are deploying this function with a 256 megabyte memory setting. To deploy the function and invoke it, we can simply call the function like it was any other Python function inside the Jupyter Notebook. Facet will automatically package and deploy the function and then after deployment, it will invoke the function and return the response back to the Jupyter Notebook as if it was any regular Python function. One of the key benefits to Facet's deployment automation is that it enables multi-platform support, where you can write a function once and then deploy it to multiple different platforms without having to make any code changes. Next, we will discuss some of the other key function management features of Facet. First of all, Facet keeps track of source code changes so that it only deploys your function whenever the source code is modified. This makes it so that you can call a function multiple times and it will only deploy it once and will only redeploy when the source code changes. The function, the figure on the right here demonstrates this, where we call the function multiple times and it deploys it once, and then we modify it and then it finally redeploys it. Next, Facet supports a simplified application development and deployment workflow where all of your work done is within a Jupyter Notebook. You do not need to touch any of the files besides the notebook. But this isn't great when you need to make more complex functions. So Facet gives you full access to all of the build and deployment scripts so that you can always customize how your functions are packaged and deployed. If you need to add dependencies, you can customize Docker files or add flags to the deployment process really easily. Facet keeps your workspace organized so that you can customize on a per function basis and have full control over your functions. While Jupyter Notebooks always use Python, you can still use functions created in other languages in Facet. You can link existing functions to the notebook and invoke them by creating empty functions like in this example. This allows Facet to be used as a testing and experimentation tool even when you are creating functions in other languages. Next, Facet includes reconfiguration functions that allow you to change function parameters without redeploying your functions. This is useful if you want to do experiments that require varying the amount of memory allocated to functions or use different Docker images over the duration of the experiment. Finally, Facet features significant quality of life features, such as automatically defining your functions on startup so that they can be immediately invoked. This is incredibly useful if you are using multiple notebooks, making it so that you do not need to copy code between them or run a whole bunch of cells in the notebook before you're able to actually do any work. You can import Facet and immediately start calling your functions that you created in the notebook. Next, we'll move on to the experimentation phase of the Facet workflow. Facet and FastRunner integrate to provide as a simplified interface to run experiments. You can define the number of runs, the number of threads to use, payloads, and the order to run them within the Jupyter Notebook. By using Facet's reconfiguration tools, you can orchestrate complex experiments that change function configurations over the duration of the experiment. After an experiment completes, the results are then loaded back into the notebook as Panda data frames, so you can immediately start doing data analysis. And that leads smoothly into the data analysis phase of Facet. Functions deployed using Facet will automatically include the serverless application analytics framework. By using our experiment client within Facet alongside SAF, we can achieve enhanced observation into the FAST platform that will not be possible with SAF alone. For example, we can calculate the tendency of functions on some platforms like IBM Cloud Functions, which is the number of function instances sharing host infrastructure. We can also calculate infrastructure state, whether it's been reused and is warmed up, or if it's the first time infrastructure has been used and it's cold, which can add to latency, which we can also calculate using a fast runner inside Facet. And then there's much more that you can also do. Because Facet is built to work with Jupyter notebooks and experiments use standard Panda data frames, you can utilize existing Python libraries to do data analysis, processing, and visualization. You can manipulate data using pandas and NumPy, can generate visualizations using Matplotlib and Plotly, do regression or more complex data processing with scikit-learn and SciPy. And you could even use libraries like TensorFlow to do more advanced machine learning, all within the same environment where you developed, deployed, and tested your functions. This slide also features some of the graphs we've previously created using Plotly inside our Facet notebook. So this is the overview of the Facet workflow. Next, we will go into the evaluation of using Facet with different clients. One of the most important decisions that researchers must make is choosing a host infrastructure to execute your experiments and invoke your functions. There are a lot of options. You could use your own personal computer or a powerful cloud virtual machine. And now that Facet works with Jupyter Notebooks, we can utilize Jupyter Notebook as a service platforms like Google Collaboratory. To evaluate each of these platforms, we deployed a sleep function to AWS Lambda. The function simply sleeps for 10 seconds and then returns. We then attempted to execute this function 1,000 times in parallel with my local PC, a C5 Metal EC2 instance, and the free tier of Google Colab. You can see the specs of each host here on this slide. First, we observed the number of concurrent function invocations each host achieved. The C5 Metal achieved the most at 450, the local PC achieved 230, while Google Colab was only able to run 31 function invocations concurrently. Using a relatively short runtime for our sleep function made it so that no host was able to achieve the maximum 1,000 function invocations. Next, we observed the round-trip latency of each host. The C5 Metal was pinned to the same availability zone as the function, so it, in theory, achieved the lowest overall latency of 345 milliseconds round-trip on average. The PC, which was on the opposite side of the United States as the function, had an average of 700 milliseconds of latency. Finally, Google Colab was once again the worst, with just under 1.5 seconds of latency on average. Next, we'll move into the conclusions of our presentation and evaluation. Overall, the goal of Facet is to provide an accessible, streamlined development environment for developers and researchers running experiments on fast platforms. For the experiment, Google Collaboratory performed the worst. This was not a surprise that it provided the lowest specifications of all of the hosts, but this does not mean Google Colab isn't still useful. It is by far the easiest to set up. You can try Facet right now in your browser by visiting this link, but it also includes other useful collaboration features and is free, making it a great option to first set up experiments in and then move to a more powerful host if you need to run large-scale experiments. So that is my presentation. Thank you for watching. Both Facet and all of our tools are open source and available on GitHub at the link shown here. I'll also post it on Slack along with the slides. And once again, you can try Facet with AWS Lambda right in your browser using Google Colab. So we will move on to any questions.
Very nice. Let's thank the speaker quickly so that we leave more time for questions. Okay, Floriment, would you like to start?
Yes, I can start. Thank you for the nice presentation.
Thank you.
I was wondering more whether, so if you are using a provider-specific FAS platform, then it usually comes, according to my knowledge, with other services. So you can, for example, push a message to Amazon queue. Have you also considered these in your framework, or is it more just these classical request reply?
We do not create, we have not created abstract, basically wrappers for services like SQS or S3. Some of them already do exist. I don't remember the name of it, but I think Apache has created an abstraction library for some cloud services, but the main focus of Facet is streamlining the deployment process. We have not created wrappers for existing services.
Yeah, it is also the question whether it matters in this case, or whether you plan to do that in the future.
Yeah, it depends on if you're making if you're deploying functions to multiple platforms and utilizing services like that.
Thank you.
Thank you.
And David?
Yeah, thank you for that talk. That was interesting. I was just curious, running tests myself in the cloud about reproducibility and trials here. If you had any thoughts on, how do you know that you have, like, those are really cool graphs, they show something really cool, but how do you know that if you deal with that, you might get something completely different if you ran it again tomorrow?
Well, isn't that always the nature of cloud platforms? They're always constantly changing, and depending on what the demand is at any given moment, performance can change over time. I don't think that was too much of a consideration in this particular test, but to account for that, you would want to run your experiments over a longer duration of time. I know that there's performance variability research of the cloud that has run the same experiment over an entire week or a month at a time, but that was not our focus here.
That's cool. Maybe it's a focus of future work too. I just know, like, ultimately decide, where do I want to deploy? And if I was a smart vendor, I'd make it so that my short experiments run really fast so that people would pick me.
Yeah, you might see a paper coming up here in an hour that might talk about that a little bit.
Okay, then Simon.
So let me start this off with saying that the tool you've built here looks really amazing, and I can think of a number of projects that would have made this a lot easier. But what I was wondering about is the number of concurrent requests you're able to push out. And I was kind of surprised that we reach a limit so quickly. Do you know where the bottleneck for this is?
I think the main issue, or the main reason why we weren't able to even achieve 1,000 concurrent function calls on the C5 Metal was that the runtime of our function was not high enough. It was only 10 seconds before it returned. So yeah, I mean,
But then if the function is running for 10 seconds, that means we're sending about 45 requests per second out, right?
Mm-hmm.
And
yeah,
I'm wondering why this is limited at quote unquote a comparatively low rate.
Yeah, I'm not exactly too sure what was happening on the platform itself, which was AWS Lambda, but it seems like at least with the C5 metal that we peaked at this one point, and then we got to a point where the early function calls we made finished, and then we just hovered around. Do I have a little, can I show up? Where we just hovered at this point where the platform wasn't like scaling up higher, and it was just taking the requests and returning them by the time that they were finishing. Maybe I should probably run this test again with gradually increasing the runtime to see at what point we do achieve the maximum. But it is a little strange that even with the C5 metal, the most powerful EC2 instance, or one of the most powerful EC2 instances we can get, that we weren't able to achieve 1,000 function calls with what, 96 cores.
In the interest of C5 is really large then.
Yeah.
Not just large, but very large, sorry.
In the interest of time, let's push this offline, but it's not uncommon for initially, technology that has high theoretical peaks to not actually reach them with the first implementations and first tryouts.
Yeah.
Later, as the technology matures. So this allows me to bring this session to a conclusion. Let's take a break until the scheduled time, so just 2-3 minutes. Stretch your legs perhaps and be prepared. Evgenia will give a very nice keynote. There is a lot of good work still coming up. And also this is the moment to put, something to drink to become cold, because we have a social session at the, okay, also good. We have a social session in, I don't know, an hour and a half or something. So a break of a couple of minutes. Okay, see you back in 2-3 minutes, 45. Evgenia, you may want to try out the slides just to see that you can share, that you can switch.
Sure. Let me start sharing and start and see how it goes. Yeah, to be ready.
Exactly. So it can always go wrong, but so far somehow things have worked well.
Well, I think after all these years, we got used to Zoom.
Not a guarantee. Every morning I try out and we have all, I don't know, 6 to 8 sessions a day, and at least one does something wrong and one does something mildly wrong. This looks very good.
Okay, but typically what it's like forgetting to open the microphone. That's the typical problem, right?
Even this could be, but also Zoom, for instance, I don't know, reset settings. If you have multiple microphones, sometimes it opens the wrong one.
That's an
multiple
issue.
cameras.
It's for those the problems of those who want to go high tech. Okay. So low tech is easy. Okay, I should be. Okay, wait a minute. See, are we having a problem?
Start.
I should not start, but sorry. Yeah, no. Give me a second. Give me a second.
Sure.
Yeah, no, but this was not supposed to be doing this. Okay, are you, can you see my screen or what's going on?
Yeah, so now we're seeing your PowerPoint, which displays the main slide and the images, images of the others on the side. Yeah.
Okay.
Okay. We'll be ready when we have to start.
Yeah, so let me go here. So you see the PowerPoint, but you don't see, okay, let me not start the slideshow because it has a few automated things, some things, and then it just goes crazy. So let's not do that.
Yeah.
I'll start the slideshow when.
Then let's see if Simon is back.
Hi. Yeah.
Would you? whom should do this? You want me to do it? I can do it.
Go for it.
Let's see. Just a sec. Yes. Okay. Then let's first try again the slides, see that it works, see that everyone is back.
Okay. Yeah, but let's yeah. Okay.
Okay. So hello everyone, welcome back. It's really my pleasure to introduce Evgenia Smirny. She needs no introduction. She is extremely well known in the performance engineering community, reliability, performance evaluation, high performance computing. The list goes on and on. The list of honors and awards is very long, so I'll just mention a few. IEEE Fellow, various Best Paper Awards, of course. I will mention one that was happening very early on, I guess, the Distinguished Associate Professorship at, what was it, Wilson and Martha Claiborne Stevens, Distinguished Associate Professor. I guess that actually built up to the full professorship in the College of William and Mary. I was surprised myself to notice that she was a visiting professor at Monash in Australia. But
regretfully, the pandemic stopped this thing.
No.
I had to go back.
Exactly when you were hoping to enjoy the
That's
place.
Right. That's right. I mean, so that was cut short by COVID.
So without further ado, she will combine machine learning inference as an application with serverless platforms. I think it's a really hot topic, and the technique to do this is very interesting. Please go ahead without other intervention.
Thank you. All right. So first of all, I'd like this is joint work with collaborators at the University of Nevada at Reno, Aksana Lee and Fen Yang, but most importantly also with Riccardo Pinciroli, who is in the audience. So in case you guys have questions on that I cannot answer on the analytical model, we've got Riccardo who is going to tell you everything you need to know. Actually on the very difficult part of this work. So this is a paper that actually I'm going to present a paper that has appeared at Supercomputing 2020. So it's about a year ago and a few months ago. So we do have the PDF of the whole work. So if you would like, details on it, you'll be most welcome to look into it. We also have some follow-up work from this, again into an even more complicated system, but this is in a second round of revision for a top conference, and regretfully we cannot announce it yet, but hopefully in a month I hope that we will be able to point to the follow-up of work of what I'm going to talk about. All right, so I'm going to machine learning as we are somehow. Yeah, here we are. Okay, so machine learning as a service, typical MLAS systems, Amazon Web Services, Microsoft Azure, Google Cloud, the typical things that they have. You build the model, you train the model, then you serve after the training, right? And then the kind of applications, you can have vision applications, speech applications, natural language applications that they go into the cloud, whichever cloud you've got, to serve them, right? And actually the kind of thing that we're going to focus here is vision applications, serving vision applications on the cloud. So traditionally, how does this work? You got servers, you got your vision application, image recognition, is this a bird, what is it? If you have a speech transcription, that's another typical application. Natural language, like what's the weather, city, sunny, if you are in a nice place or not. But this is so you have like this callable API that goes to the servers. So now what happens is that what we find is that if we have an increase in the workload burstiness, it can result in servers SLO violation. So the results can take too long, right? So this can become an issue. So the question becomes like, okay, I want Siri to answer to me fast, but how do I provision resources efficiently to make this happen? So over provisioning, right? We're computer scientists, we know exactly how this works. Hey, put more CPU cycles, they are cheap, that's the way to go. Great way, it reduces latency. However, high cost, and also not to also mention actually the energy cost. Energy sustainability issues, I mean, come on, let's face it, like, let's all be responsible citizens, okay? So the question becomes, when and how much to scale, right? So how should we do this? So reactive scaling, actually, when it is, you can do things proactively or reactively. So we're gonna talk about these things. So the Amazon SageMaker, which is actually what Amazon gives, you have, it does scale to the workload intensity. It is coarse grained, but the problem, it is too many tuning parameters, right? So here is what you've got, the requests, the nodes as a function of time. Essentially, that's what you want, to change the number of servers as a function of what is your workload and change them like in a nice way, right? The problem is the too many tuning parameters. And here's an example, a screenshot of all the parameters that you need. I mean, look at those. I mean, there are many, right? So how can I figure out the best optimal parameterization? It's very difficult, right? So we go into this case like, okay, summary, right? We have over provisioning, reactive versus proactive. And if you put to all of these things, the effect of burstiness and bursty workloads, you've got a tremendous challenge going, right? So how can we solve this thing? Well, the result of it is like, we're going to solve with an analytic model, right? I'm not going to show you this yet. We're going to show it with an analytic model that we can solve this tremendous challenge really very nicely. So let's go now. What we are going to do, we're looking actually into the performance solution of serverless. So we're going to do things on experiments on Amazon Lambda. Serverless does dynamic scaling. So the number of invocations there is the number of concurrent events. And this is like so much better than SageMaker, because on the serverless platform, they only have like really only one parameter to worry about, and this is the memory. So this is so much better than the craziness of 1,000 parameters, right? So here's what you've got. You've got the clients, they send the images to the cloud, and then eventually from Lambda, you get charged based on the number of invocations and the memory allocation, okay? So this is a lot more, let's say, controllable experiment, and then you know what's going on. Example now. So let's say that we have like this is a Twitter trace. This is the arrival process that you can have from a Twitter trace. So you can see that you have real burstiness. And on this side right here, you can have the result of the scalability. So we compare now Lambda versus SageMaker. So Lambda is the yellow line, SageMaker is the blue one. You can see that there is scalability. Now, if we're gonna go and look into latency, and now for latency, what we see is that, okay, Lambda is doing great, very flat line right here, right? But then SageMaker is not doing so great. All right, let's go into the cost. What happened with the cost? Lambda is more expensive than SageMaker, right? So the question, and again for SageMaker, we tuned perfectly. So we did all this exercise, manual exercise to tune it really very well. So the cost is still expensive. So yes, IaaS is slow in scaling, but cheap. So how about looking into a hybrid idea, right? So this is Mark. This is another idea that says like, okay, let's do a combination, a hybrid solution of those. And Mark says like, if you have a workload search, so a burst in the workload, then you go to the serverless paradigm. Again, this is super complicated because you got, you have the best of the two worlds, but you have the tremendous inconvenience of the two worlds, right? So let's see, like, if we're going to see the difference here between latency and cost. So the latency for Lambda versus Mark, you can see that Mark still is not doing so great with respect to latency because it does not have a consistent performance. When you look into the cost, again, between Lambda and Mark, still Lambda is more expensive. But also put of the terrible inconvenience of using Mark because you've got to use like really a lot of things. So if you compare the three techniques, right? These are like the things that are available state of the art. Mark is the state of the art, that does between the hybrid solution. SageMaker is what Amazon gives. And then you got Lambda, which is easy to use, right? But it is not SLO aware and the cost is expensive, right? But it's convenient, right? The convenience, that's the only thing that has the convenience there. So the question becomes like, how can we improve on Lambda? And how can we improve actually the cost of serverless? And then to be able to do that, what we did was to have the power of the analytical models. Of course, that's what I'm gonna say, because there is like math to the power, right? And queuing networks to the power. And that's what we're gonna see now, the idea how we're gonna do this thing. So batching for training is quite common. And also batching for serving is quite common. So here's how it works. So you got like a bunch of, let's say, requests. You create a batch size and you send them to the server to be served together, right? But then if you have also a batch timeout, so you have like a batch size, how many are you gonna send together to the server? I mean, let's see this thing again. Okay, so you're gonna have like a timeout. Let's say that your timeout is going to be 3, and then if you actually it's 3 seconds, okay, and then you collect like 3 images, and then okay, they go to the server, right, for serving all together. But if you don't have enough images that come during the timeout period, you just send them off because otherwise you are waiting for too long into the queue, right? So so you have like 2 things to worry about, like how big should my batch be? So how many requests should I put together before I send them to the server? And also what should be my timeout? So when should I stop this batching, right? So there's the duration and also the number of invocation. Parameters now we have to worry about. 3 parameters is the batch size, is the timeout, when should we send them off to the server, and the memory size, of course. And for these challenges, there is absolutely no support by Lambda. So we have to decide as users how it's the best way to do this. So there is parameter tuning, not crazy parameter tuning as it was for SageMaker, but depends on these parameters. We have like different performance measures, right? So again, to be able to do this thing in a smooth way, because now we have 3 parameters, we feel that there are still too many, not as crazy as SageMaker, but still too many. How can we do it nicely? So yeah, that's my answer. Queuing models, that's the way to go. And there are some problems, right? Because when we're gonna go into SLOs, queuing models do not support, they provide means. They do not give percentiles, no percentile latencies. And for SLOs, you need percentile latencies, right? The other issue here is that also we have like this infinite capacity model because you have a serverless, right? So you have essentially infinite servers, which is actually a good thing. That's something we can handle with models. And then everything you have to put like together this idea of the batching. You have to use a new model. And the next thing that you have to do, actually, you can also put the serverless. So infinite capacity enables predicting percentile latency, actually. And this is like a great thing that we saw. And actually, this is something that Ricardo figured out. He said like, hey, wow, if we have an infinite capacity, we can do percentiles and we can create some really nice performance models that can capture percentile latencies. So between knowing what the service is, knowing what the arrival is, we can come up with models that can tell us that what would be the ideal numbers of the batching parameters. All right. So two kind of optimize. So we have like two inference scenarios, two optimizations that we're going to look into. The first one is to minimize the cost subject to the SLO. And the second one, the second optimization target would be to minimize the cost. Now, workload burstiness. We would like to figure out the ideal buffer size, also the timeout, but for a workload that is bursty. Now, how do we do that? And to do it, Markov modulated Poisson arrival process is the typical technique that does that. And typically for that, we have a quiet period, a high intensity arrival period. It's what we observe. We also have some hidden transitions between the quiet and the high intensity period. And then you can build the model and you can allow the change the phase during the observed events. So you can have, a nice way to capture this behavior. So 2 cases now for the batch distribution. You would like to get the probability of the observed request to be less than the maximum batch size, and also the probability of observed request to be equal to the maximum batch size. And the nice thing is, like, we can measure the service time during lightweight profiling. And what can we do? Actually, we found with our lightweight profiling that most of we have constant service times, and this helps us tremendously into building this analytical model tremendously, because now we can have 2 cases. One is when the number of requests is less than the batch size, and the latency is the service time plus the timeout. And then when the number of requests is the maximum batch size, and then the latency is less than the service time plus the wait time. And now with this observation, we can use all the great tools of the matrix analytic methods, and then we can really apply them to this problem and figure out the ideal parameters. Now, how can we do that? Here, we put everything together. Here it is. We have the data flow. We have the serverless platform. We have like the buffer. We implemented this buffer, which is essentially the batching into an Amazon like small instance. We have the profiler, the service, the arrival, and then the actual model now that it observes everything that comes in is implemented on Amazon. And then the performance of optimizer with SLO, we figure out, the model figures out different cases of the memory and the ideal memory size to be able to deploy it. And that's what we do. So the test bed, we implemented this, again, it's on the Amazon. So we use the 4 different things like the Lambda, SageMaker, Mark, which is like the hybrid way, and also Lambda plus the ideal, which is like the best case. If you know everything, Lambda plus cherry pick the ideal memory size. The ML platforms we use, here they are, and the model. Now the workload, 2 real-world workloads is the New York City Thruway. This is a workload that identifies car plates at the New York City Thruway, and of course the Twitter workload. Both of these workloads, they are bursty. You can see that they are very different depending on the time of the day. The very first thing, of course, that we have to do, because now we're using a new model, a new performance model, is like, is it good, right? Because can we use it to do any kind of prediction? So that's the very first I'm going to show you, the validation of the analytical model. And typically for analytical models, you see validations for the averages. Here, because we care about percentiles, we see validations for the entire distribution. And you can see in 3 cases, 3 examples. Both of them, we have like great validation. I mean, you can see the red and the blue, great. The model is the blue, the experiment, the actual experiment is, I want to spend a little bit more time here, so I should not rush. Okay, the experiment mean error less than 6%. This means that we can use the analytical model accurately to predict the latency of the burst workload. And all this part of this contribution, the model and how good it was, how good it is, this is like, it's Ricardo. He's the one who did all these things and figured them out and all the detail and all the troubleshooting. And then finally, a very robust piece of software, essentially. That's how it all translated to. All right, so here we are as first experiments. The first scenario, we optimize SLO latency. Now, the normalized latency, it is the flat line right here at 1. And then the 4 different things that we check, lambda, that's the yellow line, SageMaker is the pink, batch is the blue, and the cherry pick lambda, it's the red. With the cherry pick lambda, this was done after a lot and a lot and a lot of experiments, okay? This is not viable to do. But the good news is like, if you're gonna see on the left, always batch is below the target latency, and on the right, it has the best cost, okay? It costs so much less than SageMaker, so much less than Lambda, so we're doing great. We're optimizing the latency with the minimum cost. All right, so let's go to the next one. So how does it work? How does it adapt? So on the left-hand side, we have like the batch size, and we also have the timeout. And throughout the day, the time, I mean, this is for the Twitter workload, you can see the adaptation. So batch is like quite adaptable to the workload. On the right-hand side, you're going to see the memory, how also it adapts. So you can see this dynamic adaptation being like really, really good. Now, that was if we optimize for the SLO. How about if we optimize for the cost, right? This can be another optimization problem. Let's see what happens. So this was now what we put in the optimizer. That cost is what we care about. This is on the left. We see the cost of Lambda, really good. On the right, you can see the performance, how it, again, the performance, the SLO is not the optimization target, it's the cost. But we can see that we still Lambda does well, and it still adapts its parameters to comply with the budget. Because here you have like your target is just the budget. Okay, takeaways, and this brings me to the end of the talk. But lifts the burden of resource provisioning from the developer. It dynamically adapts the batching parameters for varying workloads, and it minimizes the cost per request. So this is for a workload who is actually homogeneous, because what we are finding these like vision workloads, more of them are they are homogeneous workloads, so the service time is the same for all of them. So the question becomes, what happens when you have a service time which is not homogeneous, right? So what would you do? And this is our follow-up work, and we hope to be able to make it available really very soon, because we have some really cool results there for things like speech applications when you have short requests and long requests, and we can really show how this idea of batch can actually really work very well. So I'm done, I think, within my 25 minutes. Yay.
Perfect timing. We have exactly 5 minutes left for questions.
That's what you guys told me, right? That's what I
perfect.
did. So.
Let's start this off with a question from Murray. Are you here, Murray?
Yes, indeed. So I had a couple of thoughts again. One is that it wasn't entirely clear to me where the win came from here. Is it because it actually runs faster and costs less to do for everybody when you batch, or is it just because the charging algorithm is per invocation, so you get it cheaper from the provider?
No, you get it because you get, if you batch, it is cheaper. Because you serve, it's like it is like think of MM1 versus MMN with the same service rate, right? So you serve n requests with the same cost as one, and this is the idea of batching in machine learning.
So I understand, but it's the cost to you as a user, not the cost to the cloud provider who has to execute all those requests.
No, they execute them in with one instance, right? They execute them together. So the cost is the same. Yep.
Okay.
So you execute them as a bundle, and the cost to execute 1 or 5 is the same. It doesn't matter, both for the service provider and for the user. Yep. Right.
Oh, great. And the other thing I wondered about was if you have classes. Well, you sort of touched this at the end there, where you have classes with different amounts of work to do. But I suppose you have classes with different service level objectives.
Exactly. Well, with different service level objectives, gosh, now I don't remember. Ricardo, do you remember? It's a great thing we have another author here. So, Ricardo, do you remember? Do we have like something with different classes with different service objectives? I don't think we have considered this thing, but that's a great idea.
Yeah, can you hear me?
Yes, we can hear you. Yeah.
Till now we have not considered yet different SLOs, but only different classes with different service levels, but not different objectives.
Yeah. Different classes we have, like especially for speech recognition, you have like quick speech versus long speech, right? So that's what we focused on, a heterogeneous workload essentially. But what you're saying, Mary, is a good idea. Maybe we can do a follow-up, Ricardo. Yeah, thank you. That's a great idea. Yeah.
I also wanted to ask a question. I'm wondering where the benefit of the queuing model comes from in a scenario where you have infinite capacity, because based on my understanding, if you have a queuing model with infinite capacity, it's always going to return the service demand, right?
Yeah, exactly. So Ricardo, that's your cup of tea. Do you want to respond to this, or you want me to respond? Because you have the benefit of two people of the same work here. And actually, he's the analytical guy. You want to respond, or should I say?
I can do it.
Yeah, sure.
Actually, the benefit is the benefit here of considering the queuing model is coming from the fact that we have to account for the time that the first request and all other requests have to wait for in the other requests that are going to be collected in the same batch. Right. So basically, the only request that is not paying any waiting time is the last one, the last one before the batch is sent to the serverless platform. Yeah. But otherwise, all other requests have to pay some waiting time, and that waiting time is accounted in the queue. So for that reason, we need to account for the for the queuing time, for the waiting time, even if we have an infinite server for the...
Makes sense. So
also,
the idea is not...
If I may add something, Simon, I mean, it's also, we are unsure about what is the ideal batch size, what is the timeout, and what is the memory. So what the model allows us is to very quickly figure out the ideal, do an optimization problem by doing several runs with different parameters and figure out, okay, for these 3 parameters, boom, that's the ideal number to use. And and of course, we could do this thing when we cherry picked, and this cherry picking was extremely painful because we had to do so many experiments and then figure it out. But the model allowed us to figure these things out quickly.
Makes sense. So if I understand Ricardo correctly, the idea is not like in a traditional compute system where you analyze the waiting time for the CPU serving, but rather the waiting time in the batch buffer. Right. So I think there's quite a few more questions in the Slack channel, but in terms of time, we unfortunately need to move on. So let's thank Evgenia and Ricardo for the very interesting keynote.
Thank you. Real pleasure. I'll go into Slack and try to respond. Maybe both B and Ricardo, we should try to do that, since you guys have also the benefit of 2 people here. So let's say it's like a multi-server system, right? Yeah.
Good format.
Okay, great.
So
I should stop sharing, right? Yeah, stop sharing.
Our next talk is again from the group of Wes Lloyd. Robert, are you presenting this? Oh, sorry, we have two Roberts. Robert Schmitz, right?
Yeah, I'll be presenting with Daniel. So I will start screen sharing. Okay, hopefully everyone can see the slides.
Looks good.
Okay.
Hello, everyone. I'm Danielle Lambion, and I'll be presenting our paper characterizing x86 and ARM serverless performance variation and natural language processing case study. And I will be presenting this with Robert Schmitz. First, we'll discuss some background information for our paper. We aim to study serverless computing performance variation as cloud providers abstract platform information from end users. This abstraction leads to reduced observability when analyzing the function performance. In this paper, we specifically looked at AWS Lambda, which abstracts the processor type and tenancy of the function execution across servers. To study performance variance, we used two new features offered by AWS Lambda. First, we investigated support for multiple CPU architectures on AWS Lambda, specifically Intel x86-64 and the Graviton2 ARM64. Secondly, we harnessed the ability to deploy Lambda functions with container images using the AWS Elastic Container Registry, which supports images up to 10 gigabytes to more easily package and deploy large functions. We investigated performance variation over a 24-hour period across 4 cloud regions for each of the supported CPU architectures. CPU steal was a key metric in our investigation. While the number of tenants sharing cloud servers is often obscured, the CPU steal metric available from Linux procfs has been shown to identify resource contention, which typically correlates with workload performance degradation. CPU steal ticks are registered when a VM is ready to execute. However, the physical CPU is busy servicing work from other co-located VMs sharing the physical host or from the hypervisor itself. AWS confirmed that there is no CPU steal on AWS resources supported by the Graviton2 ARM CPU because the CPU does not use hyperthreads. Each vCPU is supported by a physical core. To give a brief overview of related works, in 2010, Shad published results for an extensive investigation on performance variation of infrastructure as a service cloud and object storage platforms on Amazon EC2. This was done prior to cloud providers reducing VM overhead. In 2016, Leitner and Zito evaluated performance variation on VMs across Amazon, Google, Azure, and IBM over 72-hour periods. In 2018, Uda and Obaseki emulated prior work by Bolani to investigate performance variation on big data workloads. In the same year, Wang explored multiple CPU types and VM configurations on function as a service platforms to produce a performance model, accounting for variation from CPU heterogeneity. And other related works found that the number of tenants sharing a server increased when scaling up concurrent requests on AWS Lambda. Ginsberg and Friedman's 2020 paper investigated diurnal performance patterns on AWS Lambda, focusing on performance for the US East 1 region over 1 week. They also contrasted performance of the US East 1 and AP Northeast 2 regions over a 48-hour period. Ginsberg and Friedman identified that there is a relationship between the CPU steal metric and function performance. They were able to demonstrate that better performing function instances could be found and leveraged with short-running performance tests to produce cost savings. Next, I will introduce the research questions from our paper. In this paper, we investigated the following research questions. Question 1, what are the performance and cost implications of adopting the ARM64 versus the Intel x86 CPU architecture for running a multi-step NLP pipeline on a commercial serverless fast platform? And question 2, what performance variation results from the use of alternative cloud regions over 24 hours, where the state of resource contention is likely to change to host a multi-step NLP pipeline on a commercial serverless fast platform? Next, we will discuss the natural language processing use case. As our performance use case, we use topic modeling. Topic modeling finds a group of words or topics that represent a data set of textual information. We perform topic modeling on a set of news headlines to generate our set of topics. Then new news headlines can query the topic model and select a best fitting topic representation for that headline. We deployed our topic modeling use case as 3 serverless functions on a single AWS Lambda function. Our first function preprocesses the training data in preparation for training the topic model. Our second function trains a latent directly allocation topic model using the preprocessed dataset of news headlines. And then our third function allowed new headlines to query the model for topics. Now I'll hand it over to Robert to describe the experimental approach.
Okay, so we deployed an x86-64 and ARM64 Lambda function in each region of our study as shown here. Each Lambda function was deployed as a container image, which was a composition of all components to run the NLP pipeline. An EC2 VM instance was deployed in each region of study to run the NLP pipeline Lambda functions for both x86 and ARM. Each function in the NLP pipeline was invoked sequentially using the AWS CLI, the serverless application analytics framework, or SAF, was leveraged to profile AWS Lambda function executions to capture server-side runtime, container state, CPU steal for the x86 architecture, and many more. For each region and architecture combination, 112 pipeline runs were executed over 24 hours. Next, we will describe our results. To investigate research question 1, we executed our NLP pipeline for 24 hours across 4 AWS regions and calculated average runtime metrics, which were used to calculate projected cost. We profiled each of our NLP pipeline functions with the serverless application analytics framework to evaluate differences in computational requirements using the US East 2 region. We measured the maximum function memory utilization by testing each function separately by making a cold function call. We profiled runtime, the average number of memory page faults per minute, and the average CPU context switch per minute on x86-64 and ARM64 as shown in this table. We can see from the figure in the table that the runtime for the pre-processing function had a faster overall runtime on the ARM's 64 architecture. The training function ran faster on x86, and the query function had a faster runtime on ARM. The calculated runtime metrics and cost savings is shown in this table. The average runtime for ARM64 was about 98% of x86-64. the standard deviation of runtime was much higher on x86-64, roughly 284% of ARM64. The coefficient of variation was larger for x86-64, roughly 279% of ARM64. AWS provides a 20% discount for the use of their Graviton 2 ARM CPUs on AWS Lambda. This discount combined with better performance on ARM64 results in the x86-64 NLP pipeline execution cost of 27.15% more on, more on x86-64 versus ARM64 for an estimated 10,000 runs. So here's a summary of our results. To investigate performance variation of our NLP pipeline in support of research question 2, we executed our pipeline continuously over the course of a regular business day across 4 regions on 3 continents on both the x86-64 and ARM64 CPU architectures. We use CPU steal as a resource contention metric for the x86 architecture. Here we show the average CPU steal, the R² for a linear regression with pipeline runtime, and finally the Pearson correlation between CPU steal and the pipeline runtime for the 4 regions in our study. Referencing our table, we found average CPU steal ticks per minute was 4.3 times more for US West 2 versus EU Central 1. These graphs depict the diurnal NLP pipeline runtime over 24 hours across 4 regions for both our CPU architectures. As we noted in our previous results, US West 2 in dark green had the slowest performance, and EU Central 1 in dark blue had the fastest performance for the x86 architecture. Overall, the ARM64 architecture performance was much more consistent as far as runtime. In this graph, we use a 2-hour sliding window to depict how the average pipeline runtime changes throughout a day. We combine the data for all 4 regions relative to local time to show the diurnal performance behavior. The graph shows the global average NLP pipeline performance for both CPU architectures. We normalize the performance so that 1.0 equals the global average ARM pipeline runtime. We observed that the NLP pipeline runtime on x86-64 processors from 10 a.m. to 12 p.m. was 6% slower in contrast to 6 a.m. to 8 a.m. and 3.3% slower on ARM processors from 2 p.m. to 4 p.m. versus 12 a.m. to 2 a.m. In summary, the NLP pipeline runtime tended to be faster outside of regular business hours on any CPU architecture and region over the course of our 24-hour study. Next, we will go through our conclusions. For research question 1, researchers and practitioners should be encouraged to adopt the ARM64 architecture on AWS Lambda when possible, due not only to the discounted cost and better performance, but also because higher resource contention on x86-64 further exacerbates the cost differential. We estimated up to 33.4 cost savings for our NLP pipeline by leveraging ARM64 instead of x86-64 in the US West 2 region. This is the region that exhibited the highest resource contention. ARM64 cost savings, however, may only be temporary if the discounts drive more users to adopt this architecture. For research question 2, researchers and practitioners running non-latency sensitive workloads may consider redirecting their workloads to leverage regions outside of regular business hours. For example, we observed a 6% global average runtime differential across 4 regions from 6 a.m. to 8 a.m. versus 10 p.m. to 12 a.m. So this concludes our presentation. If there are any questions.
All right, thank you very much for the quite interesting talk. I think there was a couple of questions from Alexandru, so let's start off with those.
Sure. So thanks for the talk. I think the topic that you're approaching is particularly difficult because performance variability has some of the most nuanced kinds of answers that I think we need to give at this moment, as opposed to the single value of merit. You need to capture everything and explain it, etc. So let me ask the more philosophical and fundamental question. Do we understand how the performance variability varies itself over time? Because it doesn't look like it's a very stable process of performance variability. And if we understand this, yeah, what are the causes? What should we be measuring?
Let me just kind of reference our paper here quick. Vary over time, you mean as far as over the course of a day, or
over even longer periods of time? So over months and years, but over at any granularity, there is performance variability, and it seems to vary in different ways. The more you change the granularity, the more it seems to vary this performance variability itself as a process.
Right. Yeah, we only studied over a day just due to cost, but we had, I think, mentioned that as a future work, we could probably extend the study longer. But we did, find a pattern that we tried to kind of outline as far as like the time of day did seem to, matter as far as like when you're running the pipeline. So as far as like tweaking other portions of the deployment, like memory and the timeout, we did tinker with those pieces also, but we kind of just wanted to lock those in for this study. So we chose a memory range that seemed to work well for our NLP pipeline. But yeah, I guess if I will get back to you as far as
no, but Robert and Daniel, as a general comment, we keep forgetting that big results in science that explain, a large process or something like this, they're actually built exactly from these kinds of use cases and studies that have to take out, at least the information on which you can start building those theories, those ideas. Right now, we don't even know how performance variability in this context really works. So again, don't undersell your work, but I'm also curious about the big picture. Yeah, so that's a bit, all sides are necessary, and you can't build a reasonable big picture. You can speculate any way you want, but you can't build a reasonable big picture without exactly the kind of work that you're doing here. Yeah, so that's how we build as a community. But I'm also curious about the long term. Okay.
Right. So let's maybe switch the slides already to the next speaker.
Sure.
But I would also ask a question. I was wondering, so if I understood correctly, the coefficient of variation is different by quite a crazy margin between ARM and x68. And this is due, if I understood you correctly, to a conceptual difference, where on the ARM there is no real resource sharing, and we have a real core for each thread. And what I'm wondering about, which goes way beyond the topic of your talk, if this isn't crazy inefficient from the provider perspective, because they're going to use a lot more resources for the same price.
Yeah, go ahead, Wes.
Oh, if I might add, the Graviton 2 ARM processor doesn't feature hyperthreading. So by design, there are no hyperthreads. And so in that sense, it is more resources on the part of the provider, but the Graviton was actually designed by AWS. So I think they're getting a discount on the hardware.
So the idea is kind of that this is almost like a generational leap between hardwares, if I understand correctly.
Well, it is certainly an alternative to x86. And one of the interesting things as well is for certain workloads, it may work better, and for others, it may actually be slower. And so it's the case where you have to just try it out and see.
All right, very interesting. And, let's start with the last talk of the day, which is called Measuring Baselines, Overheads, and Different Orchestration Mechanisms for Large, Fast Workflows. I think here to present today is George, right?
Hello, yes, I'm here with our is the candidate, Chris, so he will make the large part of the presentation, and I will be here to assist him. So can you share screen?
Yes, this works fine.
Okay. So Chris,
can I start?
Yes.
Okay. As George said, Chris and I will be presenting measuring baseline overheads in different orchestration mechanisms for large, fast workflows. Okay, so nowadays serverless computing has emerged as an alternate execution model within cloud computing and cloud infrastructures. So, and currently the size of fast applications is rather small. We know that 82% of them have only up to 5 functions in the workflow. Also, native orchestration mechanisms of fast toolkits typically present significant limitations. So problems emerge, especially when the size increases in fast workflows. And also we are curious on what is the overhead of different orchestration strategies. So the aim of this paper is threefold. First, it's the investigation and measurement of performance overheads and comparison of the delays inserted by each orchestration mode. Secondly, it's the comparison of the orchestration overhead to the actual useful computational time of the workflow. And finally, potential guidelines for application design, maybe, you know, improve performance or something like that. Okay, now let's talk about our first execution variation. It's the first observed mode we had. It's the sequence operator for OpenWhisk runtime functions. The targeted workflows are defined as function sequences directly in OpenWhisk, utilizing register to OpenWhisk functions as their main building block. So the thing here is that the execution lies on the OpenWhisk itself, and the orchestration lies on the sequence operator of OpenWhisk. So this is a figure. And finally, we have the selection rationale for this mode. It's simple, and it only involves native mechanisms. Okay, so now we present an alternate orchestration approach for fast workflows. It's Node-RED. It's a functional programming environment and runtime for event-driven applications. And it fits very well to the fast function concept. So it consists of a palette of available building nodes, as you can see on the left. And it has a variety of operations, protocol inputs, format transformation, message manipulation. And it can extend, they can be extended by arbitrary workflows. Functions can be grouped and reused, maybe. Workflow constructs can be created also. Okay. And the second observed mode, it's the function sequence in Node-RED executed as a Docker action in OpenWhisk. So there, the main idea is that all functions reside and execute inside the same environment container, which is a benefit. And the function workflow is created in Node-RED and deployed within a custom Docker function image. The selection rationale lies on the fact that runtime can act as an orchestrator as well as a function execution environment, IoT support, arbitrary workflow constructs, ability to parallelize only inside the same container. And finally, we have a third mode, which is orchestration flow inside Node-RED that invokes functions deployed on OpenWhisk environment. So there, the orchestration lies on the Node-RED flow, and the functions are deployed on OpenWhisk and are executed there. There is a small problem on that mode that it has a double billing issue, since the coordinating action needs to execute for the overall duration of the workflow execution. So the reason we selected this mode is that it had a strong resemblance in architecture with typical orchestration alternatives, where orchestration functions are used for coordination ability to parallelize. So there is a figure with some advantages and disadvantages for each mode. Some of them we discussed them already. Some of them we will see some points in the next slides. This is the setup of our experiment. Had three major points. First, we pre-created a set of functions for which execution delays are known and set primarily. Secondly, we used warm containers to avoid the cold start latency. And finally, only one client request was active at any given time. So you can see a figure there. It's the invocation happens from JMeter client, and the functions are executing consecutively. Okay. What was the interesting delay time was the IFC, interfunction communication, or orchestration delay, as we call it, which is actually the time in between two functions executing. It's not the innate function delay, it's the time in between them. As for the first mode, we created an artificial delay function. Imagine a sleep function. Okay, and it was registered as a Node.js function on OpenWhisk. We tried to put delay as an input. This delay may not be accurate in terms of the final delay in stressed Node.js environments, since it needs to be interpreted as the minimum delay to be asserted. So on the left, there is the Node.js code. Another point is that parametrically, we had the parametrically named sequences of varying numbers of functions. For example, from 1 to 25 number of functions with a step of 5. That means 5 sequence with 5 functions with 10, 15, 20, and 25. And actions were also exposed as web actions. That happened because we needed the API calls for the JMeter to interact and trigger those actions. So this is the second mode, and this is the flow of Node-RED. We created post init and post run methods in order for flow to be also executable as OpenWhisk function. This consists of a control loop that assigns delay and iteration number dynamically as input parameters. And all this flow was made as a Docker image and registered as an OpenWhisk Docker action for the Node-RED case. In the third mode, we replaced the purple variable in message delay node with an external OpenWhisk delay action. So our first data came from number of functions 1 to 25 with a step of 5, as I previously described, with innate delay, sleep delay, 1000 milliseconds. And each experiment was performed 40 times, so we had 40 repetitions. So this is the IFC graph that derived from those measurements. And we had two findings. For the first mode, we can use the average overhead time per function, given that this is independent of the functions used. And for the second and third mode, the initialization time is significantly affects the average produced as the number of functions grows. We can see that in the start. So the thing is that we need a model, and we need a breakdown between startup time and IFC time to be more accurate. So we created a model to add those things, and we did that with a simple line to detect any dependencies on the total delay, on the total flow delay time from the initialization times, intermediate function delays, and inter-function communication delays times. This is the equation that derived from that, and to optimize that, we used the ordinary least squares function with GNU Octave, and yeah, that are the three equations of the three modes. So a question arises: how does the estimated total execution differ from different function numbers and delays? So we made that graph, and as for orchestration overheads, this is a figure that presents some limitations of changing behaviors or other bottlenecks. In the near case, we can see clearly in the graph that 40 functions is considered considerably high in the code case. It's the purple one. Although it's for sure the best, and always the best in warm executions, which is the green one. And finally, orchestration overhead presented as a percentage of the actual useful function execution time is the final graph. And we can see that in many cases, overhead exceed 50 or even 100%. And we can see that Node-RED case, it's the best and presents the best benefits, the greatest benefits. Finally, for model validation, the mean absolute percentage error for the first case was 8.4%, for the second case was 19.88%, and for the third case was 6.2%, and here's the graph. We can see that in the second case, the Node-RED case, the model overestimates orchestration delays, which has the minimum absolute overheads. In order to create this validation set, we performed delays. We performed experiments with functions with delays 100, 200, and 100 milliseconds. Also, the number of functions was 1 to 50 with a step of 5 on 100 and 200 milliseconds delays. and 30 to 50 on 100 milliseconds. So we concluded, we dealt with a problem of orchestration overheads through this show. We concluded to the following. The proposed orchestration through Node-RED enables the combination of orchestration logic and function execution in the same container, minimizing the need for container spawning. Orchestration to external functions should only be used in cases of parallelization needs, and that refers to the third case. However, the combination of the two modes, near for sequential and the third case for parallelization points, would enable more optimized application orchestration. Also, baseline times, although examined at simple function chains, can be used in simulations of more complex workflow structures for the modes that support them. It's the second and third case. And also enabling easier orchestration can help increase the observed typical number of functions and lead to more sophisticated fast workflows with lower orchestration overheads. These are some data links and content. And thank you. If there are any questions.
All right. Thank you very much. Quite interesting talk. I think everybody's a little tired now after close to 4 hours of really non-stop workshop. We've somehow only planned for a total of 10 minutes of break, which we've mostly just ran over with talks that were slightly long. So I was wondering, your model you presented was actually quite accurate in some scenarios, but had some significant inaccuracies in others. And I'm wondering, do you have ideas what we could do to improve this accuracy? Is there, for example, something specific that we should measure and incorporate in the model in order to help it?
I think the case that had the highest error was for the case of the Node-RED case, which also had a larger deviation in the measurements. So can you repeat the question?
So the question is, how can we get a more accurate model? And it seems, for example, you mentioned that measurement instability is kind of high in the scenarios where we have high prediction inaccuracies. So the idea would be then, for example, to somehow get more stable measurements, and that would again in turn improve the model.
Yes, somehow, but I think this is probably the least worry for that model. So what we want to extend it basically is to include more requests, so to see what happens with multiple users. So probably that would be the first priority. Then there is also an issue with the so the number of users is something that interests us a lot now, to see how different traffic conditions can affect it. But also the estimations, could be improved. Just to mention that these are, let's say, estimations on the after removing the inner function delays. So in order not to, reduce the error artificially by including the thing that we know that takes, let's say, the static amount of time. So it's actually on the actual orchestration delay. But I think one overall problem we have with FAS in general is that it has too many parameters, and in many cases they're not really obvious, even in open source frameworks, because we typically prefer open source frameworks that we can configure them and we can see what the configuration parameter has as an outcome. Even then, I don't know if due to lack of documentation or due to complexity and so on, all these parameters are significantly hidden, and there might be some parameter that affects a lot the measurements.
I think this is kind of a theme that's running throughout the serverless talks today, that while we're hiding a lot of resources, we still have quite a lot of complexity that we kind of shoved into the configurations. All right, thank you very much for your talk. So up next, we have a short 5-minute break planned, followed by a social session. I think Alexandru is going to say a few more words on this.
Am I? Sure.
Surprise.
Now, I think it's nice. So it was a very nice day, despite that for one extra year, we're actually, doing this online rather than, in person as we are here, but physically in the same room. I really miss the other type of event, but okay, we'll see when we can actually do it. So it would be nice, to go fetch something. We'll stop the recording. So get whatever is suitable for your current environment and for the continuation of the day. And let's have a bit of a chat, see a bit what we're working on, maybe, or maybe other things. Are we going to specific conferences? I'm not sure, but let's at least enjoy a good moment together. So 2-3 minutes of a break. Don't hesitate to return and get whatever is suitable for the environment around you. I'll see you in 2-3 minutes.